Section 1. Opening and Ancient Mythology. Europa holds a special place in human curiosity, a distant moon wrapped in ice that has captivated scientists and dreamers alike. For centuries, this small world orbiting Jupiter remained a tiny point of light, yet today it stands as one of the most promising places in our solar system where life beyond Earth might exist, hidden beneath a frozen shell in a vast, dark ocean. Let yourself settle in now, somewhere comfortable, as we embark on a gentle journey across time and space to explore the complete story of this remarkable moon. We will travel together through ancient myths and early astronomical wonder, through the golden age of telescopic discovery, and onward into the modern era of robotic exploration. Along the way, we will uncover the secrets that make Europa so extraordinary, from its fractured icy surface to the hidden waters that may flow beneath. This is a story billions of years in the making, and tonight we have all the time we need to tell it properly. Our journey begins not with spacecraft or telescopes, but with stories. Long before humanity understood what moons truly were, long before we knew that other worlds existed beyond our own, ancient peoples looked up at the night sky and wove narratives to explain what they saw. Among the countless stars that decorated the heavens, a few wandered differently. These wandering stars, which we now call planets, moved against the fixed backdrop of constellations, tracing slow paths across the sky over weeks and months. The brightest of these wanderers, a steady golden light that outshone nearly everything else in the night sky, was the planet we now call Jupiter. To the ancient Greeks, this brilliant wanderer was associated with Zeus, the king of the gods, ruler of Mount Olympus, and master of thunder and lightning. The Romans later adopted this association, naming the planet after their own king of the gods, Jupiter. But our story concerns a name that predates even these astronomical connections, a name rooted in one of the most beautiful and haunting myths of the ancient Mediterranean world. This is the story of Europa, the Phoenician princess whose fate became intertwined with the divine. According to the ancient tales, Europa was the daughter of Agenor, the king of Tyre, a prosperous city along the coast of what is now Lebanon. Tyre was a centre of Phoenician civilization, a culture renowned for its seafaring prowess, its purple dyes extracted from sea snails, and its alphabet that would eventually give rise to Greek letters, and through them to the very letters you might be reading now. Europa was said to be extraordinarily beautiful, with a grace and presence that caught the attention of gods and mortals alike. One morning, as the story goes, Europa ventured with her companions to a meadow near the seashore. The young women gathered flowers, laughing and talking as the Mediterranean sun warmed the grass beneath their feet. Unbeknownst to them, Zeus himself had noticed Europa from his throne atop Olympus. The king of the gods found himself captivated by her beauty and devised a plan to approach her without frightening her away. Zeus transformed himself into a magnificent white bull, an animal of stunning appearance with a hide as pure as fresh snow and horns that gleamed like polished metal. This divine bull wandered into the meadow where Europa and her friends were gathering flowers. Rather than charging or behaving aggressively, the bull moved with unusual gentleness. It lay down upon the soft grass, regarding the young women with calm, intelligent eyes. Europa, curious and unafraid, approached the beautiful creature. She noticed how tame it seemed, how its breath was sweet and its manner peaceful. She began to stroke its flanks, marvelling at the softness of its coat. Her companions watched as she grew bolder, eventually weaving flowers into garlands and draping them over the bull's horns. The creature remained perfectly still, patient as stone, allowing her to adorn it with blossoms. Then, in a moment of playful courage, Europa climbed onto the bull's broad back. No sooner had she settled herself than the creature rose to its feet and began walking toward the shore. At first the movement was gentle, almost leisurely, but as the bull's hooves touched the water's edge, it did not stop. Instead, it waded deeper into the waves, and before Europa could leap to safety, the bull was swimming powerfully out to sea, carrying her away from everything she had ever known. Across the wine-dark waters they travelled, the bull swimming with supernatural endurance while Europa clung to its horns, the salt spray misting her face, the shoreline of her homeland shrinking to a thin line and then vanishing altogether. They journeyed across the entire Mediterranean Sea until at last they reached the island of Crete, far to the west of Phoenicia. There, on the shores of Crete, Zeus revealed his true identity to Europa. The great bull transformed before her eyes into the king of the gods himself. In some versions of the myth, Europa became the first queen of Crete, bearing Zeus several sons who would go on to become legendary figures in their own right. Among these sons was Minos, who would rule Crete and commission the famous labyrinth to contain the monstrous Minotaur. Another son, Rhadamanthus, was said to be so wise and just that after his death he became one of the judges of souls in the underworld. The myth of Europa and Zeus resonated deeply throughout the ancient world. It explained, in the symbolic language of mythology, the cultural connections between the Eastern Mediterranean and the Greek world. The Phoenicians had indeed spread their influence westward, bringing their alphabet, their trade goods, and their ideas to Greece and beyond. Europa's journey from Tyre to Crete mirrored this historical movement of culture and civilization. But the myth also gave something else to history. It gave a name. The landmass that stretched north and west of Greece, the vast continent that would eventually be home to countless nations and peoples, came to be called Europe, named after the Phoenician princess who'd been carried across the sea. Every time we speak of Europe today, every time we reference European history or culture, we are invoking the memory of that ancient story, that young woman on the back of a divine bull, crossing waters toward an unknown destiny. Centuries later, when Galileo Galilei turned his telescope toward Jupiter and discovered 4 small points of light orbiting the giant planet, the naming of these new worlds drew upon classical mythology. The German astronomer Simon Marius, who observed the moons around the same time as Galileo, proposed names from the myths associated with Zeus and Jupiter. The innermost large moon became Io, named after another figure from Greek mythology who had been loved by Zeus. The outermost became Callisto, named after a nymph who had also drawn the god's attention. The largest moon received the name Ganymede, after a beautiful Trojan prince whom Zeus had carried to Olympus. And the second moon from Jupiter, a world of ice and hidden waters, received the name Europa. The Phoenician princess who had crossed the sea now had a celestial namesake, a moon that, as we would eventually discover, conceals an ocean of its own beneath its frozen surface. The poetry of this connection is remarkable. A figure from myth associated with a journey across water now names a world that may contain more liquid water than all the oceans of Earth combined. But let us step back further still, before the myths were written, before the name Europa was first spoken, to consider how ancient peoples understood the night sky and the wandering light of Jupiter. For thousands of years before telescopes existed, human beings watched the heavens with naked eyes, tracking the movements of celestial bodies with a remarkable precision. The Babylonians, whose civilization flourished in Mesopotamia thousands of years before the Common Era, were among the most sophisticated astronomical observers of the ancient world. They recorded the movements of the planets with meticulous care, creating detailed tables that predicted where each wandering star would appear in the sky on any given night. To them, Jupiter was associated with their chief god, Marduk, the patron deity of the city of Babylon. They tracked Jupiter's 12-year cycle around the zodiac, noting how it spent roughly 1 year in each constellation before moving to the next. The ancient Egyptians also observed Jupiter, incorporating its movements into their complex religious and calendrical systems. For them, the bright wanderer was associated with Horus, the falcon-headed god of kingship and the sky. Egyptian astronomers tracked Jupiter alongside the other visible planets, weaving their observations into the fabric of their civilization's understanding of cosmic order. In ancient China, Jupiter held particular significance. Chinese astronomers called it the year star because its orbital period of approximately 12 years corresponded neatly with the 12-year cycle of the Chinese zodiac. Each year, Jupiter would reside in a different section of the sky, and this position helped mark the passage of the 12-year cycle that remains central to Chinese astrology and cultural traditions to this day. The ancient Indians, too, observed Jupiter with great interest. In Vedic astrology, Jupiter is known as Brihaspati, or Guru, and it is considered the most beneficent of all the planets. Associated with wisdom, learning, and good fortune, Jupiter's position in the sky at the moment of a person's birth was believed to influence their character and destiny. Indian astronomers developed sophisticated mathematical models to predict planetary positions, contributing to the global heritage of astronomical knowledge. Across the Pacific, the indigenous peoples of Polynesia navigated vast stretches of open ocean using the stars, including the planets. While their specific interpretations of Jupiter varied among different island cultures, the bright wanderer was certainly known and tracked by these master navigators who crossed thousands of miles of water, guided by celestial knowledge. In the Americas, the Maya developed one of the most advanced astronomical traditions of the ancient world. Their observations of Venus are particularly famous, but they also tracked Jupiter and the other visible planets, incorporating these observations into their complex calendar systems and religious practices. The Maya understood that the planets moved differently from the fixed stars, and they recorded these movements with impressive accuracy. What all these ancient traditions shared was an awareness that Jupiter was something special. It was not merely another point of light in the sky. It moved, it wandered, it followed its own path against the background of fixed stars. This movement suggested agency, intention, divinity. Across cultures separated by vast distances and with no contact between them, human beings independently concluded that the wandering stars were somehow significant, somehow different from the ordinary lights of heaven. And yet, for all their careful observations, none of these ancient astronomers could have imagined what Jupiter truly was. They could not have known that this bright point of light was actually a world vastly larger than Earth, a giant planet composed mostly of hydrogen and helium, with storms larger than our entire planet and a magnetic field of staggering power. They could not have dreamed that this wandering star was accompanied by a family of moons, miniature worlds in their own right, each with its own character and mysteries. The idea that other worlds might exist, that the points of light in the sky might be places rather than merely lights, was a concept that would take centuries to develop. The ancient Greeks did produce a few philosophers who speculated about the plurality of worlds. Democritus, the atomist philosopher, suggested that the universe might contain countless worlds, some with suns and moons of their own. Epicurus and his followers embraced similar ideas, proposing that in an infinite universe, Earth could not be the only place where matter had coalesced into a world. But these remained minority views, philosophical speculations rather than accepted knowledge. The dominant cosmological model of the ancient Western world, codified by Aristotle and later refined by Ptolemy, placed Earth at the centre of the universe. The moon, sun, planets, and stars all revolved around our world, embedded in crystalline spheres that carried them in their eternal circuits. In this model, there was no room for other worlds. The planets were not places but wandering lights, fundamentally different in nature from the Earth beneath our feet. This geocentric model persisted for more than 1,000 years, through the fall of Rome, through the long centuries of the medieval period, and into the Renaissance. It was not until the 16th and 17th centuries that a new understanding began to emerge, one that would eventually reveal Jupiter's moons to human eyes, and set us on the path toward understanding Europa as a world in its own right. The story of that transformation begins with a Polish astronomer named Nicholas Copernicus, who proposed in his work published in 1543 that the Sun, not the Earth, stood at the centre of the planetary system. In the Copernican model, Earth became just another planet, orbiting the Sun alongside Mercury, Venus, Mars, Jupiter, and Saturn. This was a revolutionary idea, one that challenged not only scientific orthodoxy, but also religious and philosophical assumptions about humanity's place in the cosmos. Copernicus himself did not live to see his ideas widely accepted. The transformation of astronomical thinking took generations, and it required new evidence that could not be explained by the old geocentric models. That evidence would come from an unexpected source, a simple optical device that would change humanity's relationship with the heavens forever. As we prepare to explore the dawn of telescopic astronomy, let yourself drift a little deeper into relaxation. Feel the weight of your body settling, your breathing slow and steady. We have journeyed through ancient myths and early astronomical traditions, tracing the long path that would eventually lead to the discovery of Europa. In the next part of our story, we will meet the individuals who first turned telescopes toward Jupiter and witnessed, for the first time in human history, the tiny points of light that would eventually be recognized as moons, as worlds, as places where the story of our solar system continues to unfold. The Princess Europa crossed the sea on the back of a divine bull, carried towards an unknown future. The moon that bears her name crosses the void of space in eternal orbit around Jupiter, carrying secrets of its own. And we, the inheritors of thousands of years of human curiosity, continue the journey of discovery that our ancestors began when they first looked up at the wandering stars and wondered what they might be. Rest now in that wondering. Let the ancient stories settle around you like a comfortable blanket. The tale of Europa is just beginning, and there is so much more to discover. But for now, simply breathe, simply rest, and let the gentle rhythm of this narrative carry you forward, just as the waters of the Mediterranean carried a princess toward her destiny, just as the invisible forces of gravity carry a frozen moon in its endless dance around the king of planets. The night sky that our ancestors watched is the same sky we see today. The light of Jupiter that fell upon Babylonian astronomers, upon Egyptian priests, upon Greek philosophers, is the same light that falls upon us now. We are connected across time by our shared wonder, our shared curiosity, our shared desire to understand the universe we inhabit. And in that connection, there is something deeply comforting, a reminder that the quest for knowledge is one of humanity's oldest and most enduring traditions. So rest easy, knowing that you are part of that tradition. The story of Europa is your story too, a chapter in the grand narrative of human discovery. And as we continue this journey together, moving from ancient myths toward modern science, from naked eye observations toward robotic spacecraft, we carry with us all those who came before, all those who looked up at the wandering stars and dared to ask what they might truly be. Section 2, The Dawn of Telescopic Discovery. The year 1609 marked a turning point in human history. Though few who lived through it could have understood just how profound that turning point would be. In the city of Padua, in northern Italy, a professor of mathematics named Galileo Galilei heard rumours of a remarkable invention that had appeared in the Netherlands. Dutch spectacle makers, craftsmen who ground lenses to help people see more clearly, had discovered that certain combinations of lenses could make distant objects appear closer. They called this device a spyglass, and news of its capabilities spread quickly across Europe. Galileo was not the first to hear of this invention, nor was he the first to attempt to build one, but he possessed a combination of practical skill and theoretical understanding that set him apart from other investigators. Within months of hearing about the Dutch spyglass, Galileo had constructed his own version, and then improved upon it significantly. Where the Dutch originals could magnify objects perhaps 3 or 4 times, Galileo's instruments eventually achieved magnifications of 20 times or more. At first, Galileo recognized the military and commercial potential of his improved spyglass. He demonstrated it to the rulers of Venice, showing how ships could be spotted at sea long before they became visible to the naked eye. The Venetian authorities were impressed, and they rewarded Galileo handsomely for his work. But Galileo's curiosity extended far beyond practical applications. He wondered what might be revealed if he turned his instrument toward the heavens. What he saw changed everything. In the autumn of 1609 and the winter that followed, Galileo conducted a series of observations that would overturn more than 1,000 years of astronomical orthodoxy. He observed the moon and discovered that its surface was not smooth and perfect, as Aristotelian philosophy had taught, but rough and mountainous, covered with craters and valleys much like the terrain of Earth. He observed the Milky Way and discovered that what appeared to the naked eye as a hazy band of light was actually composed of countless individual stars, far more than anyone had imagined. He observed Venus and discovered that it showed phases like the moon, waxing and waning as it orbited the sun, providing powerful evidence for the Copernican model of the solar system. But perhaps his most significant discovery came when he turned his telescope toward Jupiter. On the night of January 7th, 1610, Galileo observed the bright planet and noticed something peculiar. Near Jupiter, arranged in a line, were 3 small points of light that he had never seen before. At first he assumed these must be fixed stars, background objects that happened to lie near Jupiter in the sky. But when he observed Jupiter again the following night, the positions of these small lights had changed. They had moved relative to Jupiter, and they had moved together, maintaining their linear arrangement. Over the following weeks, Galileo observed Jupiter whenever the weather permitted. He watched as the small points of light shifted position from night to night, sometimes appearing on one side of Jupiter, sometimes on the other. Occasionally, one or more of them would disappear entirely, only to reappear later. And on January 13th, he spotted a 4th point of light that he had not noticed before. Galileo realized what he was seeing. These were not fixed stars at all. They were moons, small worlds orbiting Jupiter, just as our own moon orbits Earth. The implications were staggering. If Jupiter had moons of its own, then Earth was not unique in possessing a satellite. If other worlds could have moons, then the Copernican model, which treated Earth as just another planet, gained powerful support. The old Aristotelian cosmos, with Earth at the centre of everything, began to crumble. Galileo moved quickly to publish his findings. In March 1610, he released a small book titled Sidereus Nuncius, which translates to Starry Messenger. In its pages he described his observations of the moon, the Milky Way, and most importantly, the moons of Jupiter. He included careful diagrams showing the positions of the moons on different nights, documenting their orbital motions around the giant planet. The reaction to Sidereus Nuncius was immediate and intense. Some astronomers were thrilled by Galileo's discoveries, recognizing their profound significance. Others were skeptical, questioning whether the telescope could be trusted to reveal truth about the heavens. Still others were hostile, seeing Galileo's findings as a threat to established philosophical and religious doctrines. Among those who responded positively was Johannes Kepler, the great German astronomer who had already made significant contributions to understanding planetary motion. Kepler obtained a telescope of his own and confirmed Galileo's observations of Jupiter's moons. He also made theoretical contributions, working out the mathematics of how lenses bent light and produced magnified images. But Galileo was not the only observer who had turned a telescope toward Jupiter in those early months of 1610. In Germany, an astronomer named Simon Marius had been conducting his own observations, and he claimed to have seen Jupiter's moons even before Galileo. The priority dispute between Galileo and Marius would simmer for years, with each man accusing the other of various improprieties. Modern historians generally credit Galileo with the first recorded observations and the first publication, while acknowledging that Marius was conducting independent observations around the same time. But Marius made a contribution that would prove lasting in a different way. He proposed names for the 4 moons. Galileo himself had initially called the moons the Medicean stars in honour of his patron Cosimo de' Medici, the Grand Duke of Tuscany. This was a common practice at the time, naming discoveries after wealthy and powerful supporters who could provide financial backing and political protection. But the name Medicean stars never caught on widely outside of Italy. Marius, drawing on classical mythology, proposed that each moon be named after a figure associated with Zeus or Jupiter in ancient stories. The innermost moon, which orbited closest to Jupiter and moved fastest, he named Io, after a priestess of Hera, whom Zeus had loved and transformed into a cow to protect her from his jealous wife. The next moon out he named Europa, after the Phoenician princess whose story we explored earlier. The third moon, the largest of the 4, he named Ganymede, after a beautiful Trojan prince whom Zeus had carried to Olympus to serve as cupbearer to the gods. And the outermost moon he named Callisto, after a nymph and hunting companion of Artemis whom Zeus had seduced. These names, drawn from the myths of lovers and favourites of the king of the gods, seemed fitting for moons that attended the planet bearing his name. Yet for more than 2 centuries, these names were not widely used. Astronomers typically referred to the moons by numbers, calling them Jupiter 1, Jupiter 2, Jupiter 3, and Jupiter 4 in order of their distance from the planet. It was not until the mid-19th century that the mythological names proposed by Marius came into general use, and today they are the standard designations for these 4 large moons, collectively known as the Galilean moons in honour of their discoverer. Let us pause here to consider what Galileo actually saw when he observed Europa through his telescope. His instrument, though revolutionary for its time, was crude by modern standards. The lenses were imperfect, introducing distortions and coloured fringes around bright objects. The magnification, while impressive, was still limited. Through such a telescope, Europa appeared as nothing more than a tiny point of light, a dot without discernible features. Galileo could measure Europa's position relative to Jupiter, and by tracking these positions over time, he could work out the basic parameters of its orbit. He determined that Europa took approximately 3.5 days to complete one circuit around Jupiter, and he estimated its distance from the planet. But he could not see Europa's surface. He could not know that it was covered in ice, could not imagine the cracks and ridges that we now know crisscross its frozen shell. The true nature of Europa as a world, as a place with its own geography and geology, remained hidden. And yet, even as a mere point of light, Europa and its sibling moons had revealed something profound. They had shown that the universe was larger and more complex than previous generations had imagined. They had demonstrated that Earth was not the only centre of orbital motion, that other worlds could have satellites of their own. They had provided evidence supporting the Copernican revolution, helping to dislodge humanity from its assumed position at the centre of creation. The decades following Galileo's discovery were a time of rapid advancement in astronomical understanding. Kepler published his laws of planetary motion, describing how planets moved in elliptical orbits around the Sun. Christian Huygens, a Dutch scientist of remarkable breadth, made improvements to telescope design and discovered Titan, the largest moon of Saturn. Giovanni Cassini, an Italian-French astronomer, discovered 4 more moons of Saturn and made detailed observations of Jupiter's atmospheric bands and the Great Red Spot. Throughout this period, the Galilean moons remained objects of study. Astronomers refined their measurements of the moon's orbital periods and distances. They noticed that the moon's orbits were not quite circular, but slightly elliptical. They observed that the moons could pass in front of Jupiter, casting shadows on the planet's cloud tops, and could disappear behind Jupiter, hidden from view during these occultations. One particularly important application of the Galilean moons emerged from the work of Ole Rømer, a Danish astronomer working at the Paris Observatory in the 1670s. Rømer was studying the eclipses of Io, the innermost Galilean moon, timing the moments when Io disappeared behind Jupiter and reappeared on the other side. He noticed something puzzling. The timing of these eclipses varied depending on the position of Earth in its orbit around the Sun. When Earth was on the same side of the Sun as Jupiter, relatively close to the giant planet, the eclipses occurred slightly earlier than predicted. When Earth was on the opposite side of the Sun, far from Jupiter, the eclipses occurred slightly later. Rømer realized that this variation could be explained if light did not travel instantaneously, but instead took time to cross the vast distances of space. When Earth was closer to Jupiter, light from the eclipses had less distance to travel and arrived sooner. When Earth was farther away, the light had to travel farther and arrived later. From his observations, Rømer calculated the speed of light, producing the first reasonable estimate of this fundamental constant. His value was somewhat lower than the modern measurement, but it was in the right ballpark, and it demonstrated that light, though incredibly fast, was not infinitely so. This discovery, made possible by careful observations of Jupiter's moons, had implications far beyond astronomy. It contributed to our understanding of the fundamental nature of the universe and paved the way for later developments in physics, including Einstein's theory of relativity. Europa played its part in these measurements, though it was Io, with its shorter orbital period and more frequent eclipses, that provided the most useful data. Still, Europa's regular motion around Jupiter, predictable and reliable, contributed to the growing body of knowledge about the Jovian system. As the 17th century gave way to the 18th, and the 18th to the 19th, telescopes continued to improve. Larger mirrors and lenses gathered more light, revealing fainter objects and finer details. Astronomers mapped the positions of thousands of stars with increasing precision. They discovered new planets, first Uranus in 1781 and then Neptune in 1846. They catalogued nebulae and star clusters, laying the groundwork for our modern understanding of galaxies and the large-scale structure of the universe. Yet for all these advances, the Galilean moons remained essentially points of light. Astronomers could measure their orbits with exquisite precision, could predict their positions years or even centuries in advance. But the surfaces of these moons, the landscapes that might exist upon them, remained beyond the reach of even the best telescopes. The resolution required to see surface features on such small distant objects was simply not achievable with the technology of the time. This limitation meant that for more than 3 centuries, After Galileo's discovery, Europa remained a mystery. Astronomers knew it existed, knew its orbit, knew its approximate size, but they could only speculate about what it might actually be like. Some imagined it as a rocky world, perhaps similar to our own moon. Others wondered if it might have an atmosphere or even liquid water on its surface. Without the ability to see details, imagination filled the gaps where knowledge could not reach. The breakthrough would come not from larger telescopes on Earth, but from machines that travelled to Jupiter itself. The space age, which began in the late 1950s with the launch of the first artificial satellites, opened new possibilities for planetary exploration. If we could not see Europa clearly from Earth, perhaps we could send robotic emissaries to observe it up close. But that chapter of Europa's story lay far in the future from Galileo's time. For now, in the 17th century, the discovery of Jupiter's moons was revolutionary enough. It had cracked open the cosmic egg of the old Aristotelian universe, revealing a cosmos far more vast and complex than anyone had imagined. It had provided crucial evidence for the Copernican model, helping to establish the sun-centered solar system as scientific fact, and it had demonstrated the power of the telescope as a tool for discovery, an extension of human senses that could reveal truths hidden from naked eyes. Galileo himself would face difficulties in the years following his discoveries. His support for the Copernican model brought him into conflict with the Catholic Church, which at that time held that the Earth stood motionless at the centre of the universe. In 1633, Galileo was tried by the Inquisition and forced to recant his belief that the Earth moved around the sun. He spent the remaining years of his life under house arrest, forbidden from publishing or teaching his astronomical ideas. Yet the genie could not be put back in the bottle. Galileo's discoveries, published and disseminated across Europe, could not be undiscovered. Other astronomers continued to observe Jupiter's moons, continued to refine measurements, continued to build upon the foundation that Galileo had laid. The Copernican revolution proceeded despite official opposition, and within a few generations, the heliocentric model had become the accepted scientific consensus. Europa, that small point of light orbiting Jupiter, had played its part in this transformation. It was one of 4 witnesses testifying to the complexity of the cosmos, one of 4 small worlds whose existence challenged ancient assumptions and opened new horizons of understanding. Though it would be centuries before we learned what Europa truly was, its discovery marked the beginning of a journey that continues to this day. As you rest now, consider the courage it took for Galileo to publish his findings, knowing the controversy they would provoke. Consider the patience required to observe Jupiter night after night, tracking the tiny points of light as they shifted position. Consider the leap of imagination needed to recognize those points of light as moons, as worlds in their own right. We are the inheritors of that courage, that patience, that imagination. Every time we look up at the night sky, every time we wonder about distant worlds, we are continuing the work that Galileo began more than 4 centuries ago. And Europa, that frozen moon with its hidden ocean, remains one of the most tantalizing targets of our ongoing exploration. A world that may yet reveal secrets beyond anything Galileo could have dreamed. The telescope opened a window onto the universe, and through that window Europa first came into human view. It was only a glimpse, a tiny dot of light beside a larger dot representing Jupiter. But that glimpse was enough to change everything, to set us on a path of discovery that would eventually reveal Europa as one of the most fascinating and potentially important worlds in our solar system. Rest now in the knowledge that the universe is vast and full of wonders. Let the story of Galileo and his telescope settle into your mind like starlight settling into the lens of an instrument pointed at the sky. We have much more to explore, many more chapters of Europa's story to unfold. But for now, simply breathe, simply rest, and let the gentle rhythm of discovery carry you forward into the next phase of our journey. The night sky that Galileo observed is the same sky we see today. Jupiter still shines as a bright wanderer among the fixed stars, and Europa still orbits faithfully around it, completing one circuit every 3.5 days, just as it did when Galileo first spotted it. In that continuity, there is something deeply reassuring, a reminder that the universe operates according to reliable laws, that the dance of moons around planets continues regardless of human affairs, that the cosmos is stable and enduring even as our understanding of it grows and changes. So let yourself drift, comfortable and at ease as we prepare to move forward through the centuries. The age of telescopic discovery had begun, and Europa had been revealed to human eyes. But the full story of this remarkable moon was only beginning to unfold. There were centuries of observation ahead, centuries of gradual improvement in our instruments and our understanding. And eventually, there would be spacecraft, robotic explorers that would travel to Jupiter and see Europa as no human eye had ever seen it before. That story awaits us in the chapters to come. For now, rest in the wonder of discovery, in the knowledge that a single invention, a simple arrangement of lenses in a tube, could open windows onto worlds that had been hidden since the beginning of time. The universe is generous with its secrets, revealing them to those who look carefully and think deeply. Europa was one such secret, a moon hiding in plain sight until the right instrument and the right observer came together to bring it into view. And now that we have seen it, we cannot look away. Europa calls to us across the void, inviting us to learn more, to explore further, to uncover the mysteries that lie beneath its icy surface. That invitation has been extended for more than 400 years, and we are still responding to it, still sending our instruments and our imagination outward to meet this remarkable world. End of section 2. Word count, approximately 2,900 words, running total 5,700 words. Section 3. Centuries of ground-based observation. The centuries that followed Galileo's discovery were a time of patient accumulation, a long period during which astronomers gradually refined their understanding of Jupiter's moons through countless hours of careful observation. While no single breakthrough matched the drama of Galileo's initial discovery, the steady progress of these years laid essential groundwork for everything that would follow. Each generation of astronomers added something to our knowledge, building a foundation upon which modern exploration would eventually stand. In the decades immediately following Galileo's work, telescopes improved steadily. Craftsmen learned to grind larger and more precise lenses, reducing the distortions that had plagued earlier instruments. The reflecting telescope, which used mirrors rather than lenses to gather and focus light, was invented independently by several individuals in the mid-17th century, with Isaac Newton producing one of the most successful early designs. These new instruments opened fresh possibilities for astronomical observation. Giovanni Cassini, whom we mentioned briefly before, made particularly important contributions to our understanding of the Jovian system. Working at the Paris Observatory in the 1660s and 1670s, Cassini observed Jupiter with some of the finest telescopes available at the time. He studied the planet's atmospheric bands, those alternating stripes of lighter and darker clouds that circle Jupiter parallel to its equator. He tracked the Great Red Spot, a massive storm that had been observed by other astronomers and that continues to rage on Jupiter to this day. And he made careful measurements of the Galilean moons, refining our knowledge of their orbits. Cassini also observed something intriguing about the way the Galilean moons moved. He noticed that the 3 inner moons Io, Europa, and Ganymede seem to be locked in a special relationship. For every orbit that Ganymede completed around Jupiter, Europa completed almost exactly 2 orbits, and Io completed almost exactly 4. This meant that the 3 moons regularly lined up in particular configurations, their gravitational influences reinforcing each other in predictable ways. This relationship, which would later be called the Laplace resonance after the French mathematician Pierre-Simon Laplace, who analysed it in detail, has profound implications for Europa. The gravitational tugging between the moons, combined with Jupiter's immense pull, creates tidal forces that flex and stretch Europa's interior. This tidal heating, as we will explore in later sections, is likely responsible for maintaining the liquid ocean that scientists believe exists beneath Europa's icy surface. The observations that Cassini and later astronomers made about orbital resonances were early clues to processes that would not be fully understood for centuries. As the 18th century progressed, astronomers continued to refine their measurements. William Herschel, the German-born British astronomer who discovered Uranus in 1781, also observed the Galilean moons and attempted to estimate their sizes. His methods were crude by modern standards, relying on comparisons of brightness and assumptions about how reflective the moon's surfaces might be. But his work represented the first serious attempts to characterize the physical properties of these distant worlds, to move beyond mere orbital mechanics and begin understanding what the moons themselves might be like. The 19th century brought new tools to astronomical observation. Spectroscopy, the analysis of light broken into its component wavelengths, emerged as a powerful technique for studying the composition of celestial objects. When light passes through a prism or diffraction grating, it spreads out into a rainbow of colours. But this rainbow is not smooth and continuous. Dark lines appear at specific wavelengths, corresponding to elements that have absorbed light at those particular frequencies. By analysing these absorption lines, astronomers could determine what elements were present in the atmospheres of stars and planets. Applying spectroscopy to the Galilean moons proved challenging. These moons are small and faint, reflecting only a tiny fraction of the sunlight that falls upon them. Gathering enough light to produce a useful spectrum required large telescopes and long exposure times. Nevertheless, by the late 19th and early 20th centuries, astronomers had begun to obtain spectroscopic data from Europa and its sibling moons. The results were intriguing but difficult to interpret. The spectra showed features that suggested the presence of water ice on Europa's surface, but the evidence was not conclusive. The moons were simply too far away and too small for ground-based telescopes to reveal their secrets clearly. Astronomers could make educated guesses about surface composition, but confirmation would have to wait for closer observations. Meanwhile, measurements of the moon's densities provided another piece of the puzzle. By carefully tracking the moon's gravitational effects on each other and on passing spacecraft, astronomers could estimate their masses. Combined with size estimates derived from occultation measurements, when a moon passed in front of a star and briefly blocked its light, these mass estimates allowed calculation of average density. The densities of the Galilean moons told an interesting story. Io, the innermost moon, had a density suggesting a rocky composition, similar to the rocky planets of the inner solar system. Callisto, the outermost, had a much lower density, indicating a significant fraction of ice mixed with rock. Ganymede and Europa fell in between, with Europa showing a density consistent with a rocky interior surrounded by a substantial layer of water ice. These density measurements hinted at the structure that later missions would confirm. Europa appeared to be a differentiated body, meaning that heavier materials had sunk toward its centre, while lighter materials floated toward the surface. A rocky core, perhaps with an iron-rich inner core, was surrounded by a mantle of water in some form, either liquid, solid, or both. The exact arrangement of these layers remained uncertain, but the basic picture was beginning to emerge. Photometric observations, measurements of how the moon's brightness changed as they orbited Jupiter, provided additional clues. Astronomers noticed that Europa was remarkably bright, reflecting a high percentage of the sunlight that struck it. This high albedo, as reflectivity is technically called, was consistent with a surface covered in clean water ice. Dirty ice or rocky surfaces would appear much darker. Europa's brightness suggested that its surface was relatively fresh and uncontaminated, though the reasons for this freshness remained unclear. The 20th century brought continued improvements in telescope technology. Larger mirrors gathered more light, and new detector technologies replaced the human eye, and photographic plates with electronic sensors capable of measuring light with unprecedented precision. Adaptive optic systems, which use deformable mirrors to correct for the blurring effects of Earth's atmosphere, allowed ground-based telescopes to achieve resolutions approaching those of space-based instruments. Yet even with these advances, Europa remained frustratingly indistinct when viewed from Earth. The Moon is roughly the size of our own Moon, but it orbits Jupiter at a distance of more than 600 million kilometers from Earth at its closest approach. At such distances, even the most powerful telescopes could reveal only the grossest features. Europa appeared as a small disk, its surface marked by vague light and dark patches that hinted at geological complexity without revealing details. Astronomers could see that Europa's surface was not uniform. Some regions appeared brighter than others, suggesting variations in surface composition or texture. But the nature of these variations remained mysterious. Were the darker regions areas where rocky material had been exposed? Were they places where the ice had been altered by radiation or chemical processes? Without higher resolution images, these questions could not be answered. The limitations of ground-based observation created a hunger for closer views. As the space age dawned in the late 1950s and early 1960s, planetary scientists began to dream of sending spacecraft to the outer solar system. The technology was daunting. Jupiter orbits the Sun at more than 5 times Earth's distance, meaning that spacecraft would need to travel for years to reach it. The radiation environment near Jupiter was known to be intense, posing challenges for electronic systems, and communication across such vast distances would be difficult, with signals taking tens of minutes to travel between Earth and Jupiter. But the potential rewards were enormous. Close-up images of Jupiter and its moons could answer questions that had puzzled astronomers for centuries. Instruments aboard spacecraft could measure magnetic fields, radiation levels, and particle populations in ways impossible from Earth. The Galilean moons, those 4 worlds that had been points of light for so long, could finally be revealed as the complex and fascinating places they truly were. The first missions to the outer solar system were the Pioneer spacecraft, launched in the early 1970s. These hardy probes would be the first human-made objects to venture beyond the asteroid belt, the first to encounter Jupiter up close, the first to return images of Europa from nearby. Their story marks the beginning of a new chapter in our exploration of this remarkable moon. But before we turn to those missions, let us pause to appreciate the centuries of patient work that preceded them. From Galileo's first glimpse through his crude telescope to the sophisticated observations of the 20th century, generations of astronomers had slowly built our understanding of Europa. They had measured its orbit with exquisite precision, estimated its size and density, detected hints of water ice on its surface, and recognized the orbital resonances that would prove so important for understanding its internal heat. None of these astronomers ever saw Europa as more than a point or small disk of light. None of them could have imagined the fractured ice plains, the reddish-brown streaks, the chaos terrain that spacecraft would eventually reveal. Yet their work was essential. They established the framework within which later discoveries would make sense. They asked the questions that spacecraft would eventually answer. Science progresses through the accumulation of knowledge across generations. Each astronomer who observed Europa, from Galileo in 1610 to the planetary scientists of the 1960s, added something to our collective understanding. They were links in a chain of inquiry that stretches back centuries and continues to this day. When we send spacecraft to Europa, when we analyse the data they return, we are building upon foundations laid by observers who could only dream of such close encounters. As you rest now, consider the patience required for this kind of work. Centuries of observation, thousands of nights spent at telescopes, countless measurements carefully recorded and analysed. Progress was slow, measured in increments rather than leaps. But it was real progress nonetheless, a gradual illumination of mysteries that had been dark since the formation of the solar system. Europa waited through all those centuries, orbiting Jupiter in its eternal dance, its secrets locked beneath a shell of ice. The moon did not know it was being watched, did not care about the theories astronomers developed to explain its brightness or density. It simply existed, a world unto itself, following the laws of physics that govern all things. And now, as we prepare to explore the space age and the missions that would finally reveal Europa's true face, let us carry with us the appreciation for those who came before. They could not travel to Jupiter, could not send robots to photograph its moons, but they did what they could with the tools they had, and their work made everything that followed possible. The story of Europa is a story of human curiosity and persistence, of questions asked and gradually answered over generations. It is a story that connects Galileo's first observation to the sophisticated spacecraft that orbit Jupiter today. And it is a story that is still being written, with new chapters unfolding as we continue to explore this fascinating moon. Rest now in that continuity, that sense of connection across time. The astronomers of the past are gone, but their work lives on in our understanding, and the astronomers of the future will build upon what we learn today, carrying the story of Europa forward into centuries we cannot yet imagine. The night sky is patient. It reveals its secrets slowly to those who watch carefully and think deeply. Europa has been revealing its secrets for more than 400 years, and it has many more still to share. The journey continues, and we are privileged to be part of it. End of section 3. Word count, approximately 2,200 words. Running, total, 7,900 words. Section 4. The Pioneer Missions, First Visitors. The early 1970s marked the beginning of humanity's direct exploration of the outer solar system. After more than 3.5 centuries of observing Jupiter and its moons from the distant vantage point of Earth, we were finally ready to send emissaries across the vast gulf of space that separated us from the giant planet. These first visitors were the Pioneer spacecraft, modest vehicles by later standards, but revolutionary for their time, carrying human curiosity farther from home than any object had travelled before. Pioneer 10 launched from Cape Canaveral on March 2, 1972, atop an Atlas Centaur rocket. The spacecraft was relatively small, weighing only about 260 kilograms, but it carried a suite of instruments designed to study the interplanetary medium, the asteroid belt, Jupiter's radiation environment, and the planet itself. It also carried something else, a gold anodized aluminum plaque depicting a man and woman a diagram of our solar system, and other information intended to communicate something about humanity to any intelligent beings who might someday find the spacecraft drifting through interstellar space. The journey to Jupiter took nearly 2 years. Pioneer 10 crossed the asteroid belt, the region between Mars and Jupiter where millions of rocky bodies orbit the Sun, and scientists watched anxiously to see whether the spacecraft would survive the passage. Some had worried that the asteroid belt might be too dense with debris, that collisions with small particles might damage or destroy the probe. But Pioneer 10 emerged unscathed, demonstrating that the asteroid belt was far emptier than pessimistic predictions had suggested. On December 3, 1973, Pioneer 10 made its closest approach to Jupiter, passing within about 130,000 kilometers of the planet's cloud tops. The encounter was brief but productive. The spacecraft's instruments measured Jupiter's magnetic field, finding it to be far more powerful than Earth's, a vast magnetosphere extending millions of kilometers into space. They detected intense radiation belts, regions where charged particles were trapped by Jupiter's magnetic field and accelerated to tremendous energies. And they captured images of Jupiter and its moons, the first close-up photographs ever taken of these distant worlds. The images of Europa from Pioneer 10 were modest by later standards. The spacecraft's imaging system was designed primarily for studying Jupiter itself, and the Galilean moons were secondary targets. Europa appeared in several frames, but the resolution was limited, showing the moon as a disk with some hints of surface features, but nothing that could be clearly interpreted. Still, these were the first photographs of Europa taken from nearby, the first time human eyes had seen the moon as anything more than a point of light or a tiny blurry disk. Pioneer 11 followed its sibling to Jupiter, launching on April 5, 1973, and arriving at the giant planet on December 2, 1974. This second Pioneer mission was designed to complement the first, approaching Jupiter from a different angle and gathering additional data about the planet and its environment. Pioneer 11 also served as a pathfinder for future missions, testing a trajectory that would use Jupiter's gravity to redirect the spacecraft towards Saturn. The Pioneer 11 encounter with Jupiter provided additional images and measurements, further refining our understanding of the Jovian system. Like its predecessor, Pioneer 11 captured images of Europa, though again the resolution was limited. The spacecraft confirmed the intense radiation environment near Jupiter, information that would prove crucial for planning future missions. Any spacecraft venturing close to Jupiter would need to be hardened against radiation, its electronics protected from the damaging effects of high-energy particles. What did the Pioneer missions reveal about Europa specifically? In truth, not very much. The images showed a bright, icy world, consistent with ground-based observations, but they lacked the resolution to reveal surface features in detail. Scientists could see that Europa's surface was relatively smooth compared to the heavily cratered surfaces of the Moon and Mercury, but they could not determine why. The lack of visible craters was puzzling, suggesting either that Europa's surface was young, constantly renewed by some geological process, or that the imaging resolution was simply too poor to detect craters that were actually present. The Pioneer missions were reconnaissance flights, quick passes through the Jovian system, designed to gather basic data and demonstrate that spacecraft could survive the journey. They were never intended to provide detailed studies of individual moons. That task would fall to later missions, spacecraft specifically designed for extended exploration of Jupiter and its satellites. But the pioneers accomplished something perhaps even more important than their scientific findings. They proved that the outer solar system was accessible. They showed that spacecraft could cross the asteroid belt, survive Jupiter's radiation environment, and return valuable data from distances that had seemed impossibly remote just a few decades earlier. They opened a door that would never close again. The success of the Pioneer missions energized planning for more ambitious expeditions. Even as Pioneer 10 and 11 were en route to Jupiter, engineers and scientists were developing the next generation of outer solar system explorers. These would be the Voyager spacecraft, far more capable than the Pioneers, carrying more sophisticated instruments and designed for extended missions that would visit multiple planets. The Pioneers also demonstrated the value of gravity assists, using a planet's gravitational field to change a spacecraft's trajectory and speed. Pioneer 11's Jupiter encounter redirected the spacecraft towards Saturn, which it would reach in 1979. This technique would become essential for outer solar system exploration, allowing spacecraft to visit multiple destinations on a single mission and to reach distances that would otherwise be impractical. As Pioneer 10 and 11 continued outward after their Jupiter encounters, they became the first human-made objects to leave the inner solar system entirely. Pioneer 10 crossed the orbit of Neptune in 1983, becoming the first spacecraft to venture beyond all the major planets. Both Pioneers continued transmitting data for years, their signals growing fainter as they receded into the darkness. Pioneer 10's last weak signal was received in 2003, when the spacecraft was more than 12 billion kilometers from Earth. Both Pioneers are now drifting silently through interstellar space, carrying their golden plaques toward the stars. But before they departed the Jovian system, the Pioneers had set the stage for everything that would follow. They had proven that Jupiter could be reached and studied. They had revealed the challenges that future missions would face, particularly the intense radiation that bathed the inner moons. And they had whetted appetites for more detailed exploration, for images and measurements that could answer the questions their brief encounters had raised. Europa, glimpsed briefly by the Pioneer cameras, remained largely mysterious. The images showed a world that was clearly different from the rocky, cratered bodies that dominated the inner solar system, but the details were maddeningly unclear. Scientists could see that Europa was bright, confirming the high albedo that ground-based observations had suggested. They could see that its surface appeared relatively smooth, lacking the obvious impact basins that scarred the Moon and Mercury. But what processes had created this smooth surface? What lay beneath the ice that seemed to cover the Moon? These questions would have to wait for better instruments and closer approaches. The Pioneer missions also provided valuable data about the environment that Europa inhabited. The radiation measurements were particularly important. Jupiter's magnetic field, the most powerful of any planet in our solar system, traps charged particles from the solar wind and from volcanic emissions from Io, creating intense radiation belts that extend throughout the inner Jovian system. Europa orbits within these radiation belts, its surface constantly bombarded by high-energy electrons and ions. This radiation environment has profound implications for Europa. On one hand, it poses challenges for any spacecraft attempting to study the Moon up close. Electronic systems can be damaged or destroyed by radiation, and even hardened components have limited lifetimes in such harsh conditions. On the other hand, the radiation may play important roles in Europa's chemistry, breaking apart water ice molecules on the surface and creating reactive compounds that could potentially serve as energy sources for life. The Pioneer data helped scientists begin to understand this complex environment, though many details would remain unclear until later missions could make more comprehensive measurements. The radiation levels were higher than some had predicted, a sobering finding that influenced the design of subsequent spacecraft. Any mission hoping to spend extended time near Europa would need robust radiation protection. As the Pioneer spacecraft receded from Jupiter and continued their journeys toward the outer reaches of the solar system and beyond, the scientific community turned its attention to the next phase of exploration. The Voyager missions were already in development, promising far more detailed observations of Jupiter and its moons. The brief glimpses provided by the pioneers had only increased the desire to see more, to understand these distant worlds in greater depth. For Europa, the pioneer encounters were just the beginning. The moon had been photographed from nearby for the first time. Its existence as a real place rather than a mere point of light confirmed in the most direct way possible. But the true revelations were yet to come. The Voyagers would show us Europa's fractured surface in unprecedented detail, raising questions that would drive decades of subsequent exploration. And the Galileo mission, still years in the future, would transform our understanding of this icy moon entirely. Rest now as we prepare to move forward in time, from the pioneering first encounters of the early 1970s to the more detailed explorations that followed. The Pioneer spacecraft blazed a trail that others would follow, demonstrating that the outer solar system was within our reach. Europa waited patiently, as it had waited for billions of years, its secret still largely hidden, but no longer entirely beyond our grasp. The distance between Earth and Jupiter is vast, but human ingenuity had bridged it. The Pioneer missions proved that we could send our instruments across that gulf, could gather data from worlds that our ancestors had known only as wandering lights in the night sky. This was a profound achievement, a milestone in the long story of human exploration and discovery. And Europa, that small icy moon named after a mythological princess, had become a target of scientific interest. The smooth, bright surface glimpsed by the pioneers hinted at processes unlike anything seen elsewhere in the solar system. What forces had shaped this world? What might lie beneath its frozen shell? These questions, raised by the first fleeting encounters, would drive exploration for decades to come. The pioneers had opened a door. Now it was time for others to walk through it, to explore the wonders that lay beyond. The Voyager spacecraft were ready to continue the journey, carrying more sophisticated instruments and the accumulated knowledge of the pioneer encounters. Europa's story was about to enter a new chapter, one that would reveal the moon as one of the most intriguing and potentially important worlds in our solar system. End of Section 4. Word count, approximately 2,750 words running. Total, 10,650 words. Section 5. Voyager's Revelation, a World of Ice. The late 1970s brought a rare celestial alignment, a configuration of the outer planets that occurs only once every 175 years. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a spacecraft launched from Earth could visit all four giants in a single mission, using the gravity of each planet to redirect its trajectory toward the next. This alignment, recognized by aerospace engineer Gary Flandreau in 1965, presented an opportunity too valuable to miss. NASA responded with the Voyager program, an ambitious pair of spacecraft designed to take full advantage of this planetary alignment. Voyager 1 and Voyager 2 were far more capable than their pioneer predecessors, carrying 11 scientific instruments each, including high-resolution cameras that could capture detailed images of planets and moons. The spacecraft were built to last, designed to continue functioning for years as they travelled from one planetary encounter to the next. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th of the same year. Despite launching second, Voyager 1 was placed on a faster trajectory that would bring it to Jupiter first. This seemingly counterintuitive naming reflected the mission's priorities, with Voyager 1 designated as the primary spacecraft for the Jupiter and Saturn encounters. The journey to Jupiter took about 18 months. During this time, the spacecraft's instruments were tested and calibrated, and scientists prepared for the flood of data that the encounters would produce. The Pioneer missions had provided a preview of what to expect, but everyone knew that the Voyagers would see far more than the Pioneers ever could. Voyager 1 arrived at Jupiter in March 1979, beginning a close encounter that would last several weeks as the spacecraft approached, passed through the Jovian system, and then receded. The images that streamed back to Earth were breathtaking. Jupiter's atmosphere was revealed in stunning detail, with swirling storms, intricate cloud patterns, and the great red spot shown more clearly than ever before. But it was the moons that truly captured the imagination. Io, the innermost Galilean moon, proved to be one of the most surprising objects in the solar system. Voyager 1 captured images of active volcanoes on Io's surface, plumes of material rising hundreds of kilometers above the moon. This was the first discovery of active volcanism beyond Earth, and it transformed our understanding of how worlds could remain geologically active. The tidal heating that powered Io's volcanoes, caused by the gravitational tug-of-war between Jupiter and the other Galilean moons, would prove crucial for understanding Europa as well. Ganymede and Callisto, the two outer Galilean moons, revealed themselves as icy worlds with ancient, heavily cratered surfaces. Ganymede showed evidence of past geological activity, with regions of grooved terrain that suggested the surface had been deformed and reshaped at some point in its history. Callisto appeared more static, its surface a record of billions of years of impact bombardment with little evidence of internal activity. And then there was Europa. The Voyager 1 images of Europa were revelatory. Instead of the heavily cratered surface that might be expected of an ancient, geologically dead world, Europa displayed something entirely different. Its surface was remarkably smooth on a large scale, with very few impact craters visible. This smoothness suggested that Europa's surface was young, constantly renewed by some process that erased the scars of cosmic bombardment. But the most striking features were the lines. Europa's surface was crisscrossed by an intricate network of dark lines, some stretching for hundreds or even thousands of kilometers across the moon's face. These lineae, as scientists would call them, formed complex patterns that resembled nothing seen elsewhere in the solar system. Some were relatively straight, while others curved and intersected in elaborate ways. The pattern suggested a surface that had been fractured and refractured over time, though the forces responsible for this fracturing were not immediately clear. The colour of Europa's surface also drew attention. While much of the moon appeared bright white, consistent with clean water ice, other regions showed reddish-brown discoloration. These darker areas seemed to be associated with some of the linear features, suggesting that material from below the surface might have been exposed or deposited along the fractures. What this material might be remained uncertain, but its presence hinted at chemical complexity beneath the icy shell. Voyager 2 arrived at Jupiter in July 1979, 4 months after its sibling. Its trajectory brought it closer to Europa than Voyager 1 had approached, providing even more detailed images of the moon's remarkable surface. The additional coverage confirmed and extended the findings from Voyager 1. Europa was indeed a world of ice, but it was far from a simple frozen ball. Its surface recorded a history of dynamic processes, of fracturing and resurfacing that continued to puzzle scientists. The Voyager images allowed scientists to begin mapping Europa's surface features. They identified different types of terrain, from relatively smooth plains to regions of chaotic, disrupted ice. They traced the linear features, noting how some appeared to be ridges rising above the surrounding surface, while others seemed to be troughs or fractures. They measured the sizes and distributions of the few impact craters that were visible, using these to estimate the age of the surface. The crater counts were particularly significant. On airless bodies like the Moon and Mercury, impact craters accumulate over time, providing a record of the bombardment history of the solar system. Older surfaces have more craters, while younger surfaces have fewer. Europa's surface showed remarkably few craters, suggesting that it was geologically young, perhaps only tens of millions of years old. In a solar system that is more than 4 billion years old, this was extraordinarily recent, implying that whatever processes resurfaced, Europa was still active, or had been active until very recently. What could be resurfacing Europa? The Voyager scientists considered several possibilities. Perhaps cryovolcanism, volcanic activity involving water or other volatile compounds, rather than molten rock, was erupting onto the surface and covering older terrain. Perhaps the ice shell was being deformed by tidal forces, with warmer ice from below rising to replace colder ice at the surface. Perhaps the linear features themselves represented places where the ice had cracked apart, and new material had welled up to fill the gaps. All of these ideas pointed toward a crucial question. What lay beneath Europa's icy surface? The smoothness of the terrain, the youth of the surface, the complex patterns of fractures and ridges, all suggested that something was happening inside Europa, some source of heat or energy that kept the moon geologically active. Could there be liquid water beneath the ice? Could Europa harbour a subsurface ocean? The idea of a liquid water ocean inside Europa was not new. Theorists had speculated about such a possibility even before the Voyager encounters, based on calculations of tidal heating and the moon's density. But the Voyager images provided the first direct evidence that something unusual was happening at Europa, that this was not simply a frozen dead world but an active and dynamic one. The implications were profound. Liquid water is considered essential for life as we know it. If Europa possessed a subsurface ocean, it might also possess the conditions necessary for life to exist. This was a revolutionary idea, suggesting that the search for extraterrestrial life should not be limited to planets in the habitable zones of stars, but might extend to moons orbiting giant planets in the cold outer reaches of solar systems. Of course, the Voyager data could not confirm the existence of a subsurface ocean. The spacecraft had made brief flyby encounters, capturing snapshots of Europa's surface, but unable to probe beneath the ice. The evidence was suggestive, but not conclusive. Confirming or refuting the ocean hypothesis would require more detailed investigation, measurements that could peer below the surface and reveal what lay hidden there. The Voyager encounters also provided data on Europa's other properties. The spacecraft measured the moon's gravitational field, refining estimates of its mass and density. They detected no significant atmosphere, confirming that Europa was essentially airless, its surface exposed directly to the vacuum of space and the harsh radiation of Jupiter's magnetosphere. They measured temperatures on the surface, finding it to be extremely cold, around -160 degrees Celsius on average, though with variations depending on location and time of day. These measurements painted a picture of a world that was hostile by earthly standards, but potentially habitable by the standards of astrobiology. The surface was frigid and bathed in radiation, but beneath the ice conditions might be very different. A liquid water ocean, warmed by tidal heating and insulated by the ice shell above, could provide a stable environment where life might conceivably exist. The Voyager missions continued beyond Jupiter, with both spacecraft proceeding to Saturn and Voyager 2 going on to visit Uranus and Neptune as well. These subsequent encounters produced their own discoveries and revelations, expanding our knowledge of the outer solar system enormously. But for Europa, the Voyager encounters marked a turning point. The moon had been transformed from a mysterious point of light into a known world with distinctive features and tantalizing possibilities. The images from Voyager sparked intense scientific interest in Europa. Researchers pored over the photographs, mapping features, developing theories and arguing about interpretations. The linear features, the smooth plains, the reddish discoloration, the lack of craters, all became subjects of detailed study. Papers were published, conferences were held, and Europa rose in prominence as a target for future exploration. But the Voyager data, as valuable as it was, had limitations. The spacecraft had made brief flybys, capturing images from distances of tens of thousands of kilometers. The resolution, while far better than anything achieved from Earth, was still insufficient to reveal small-scale features. Many questions remained unanswered, and some could not even be properly asked until more detailed observations became available. The scientific community began to advocate for a dedicated mission to Jupiter, one that would orbit the planet and make repeated close passes of its moons. Such a mission could study Europa in far greater detail than the Voyagers had achieved, mapping its surface at high resolution, probing its interior with gravity measurements and other techniques, and searching for direct evidence of a subsurface ocean. This advocacy would eventually bear fruit in the Galileo mission, which we will explore in the next section. But the path from Voyager to Galileo was long and winding, marked by technical challenges, budget constraints, and the vagaries of space policy. Nearly 2 decades would pass between the Voyager encounters and Galileo's arrival at Jupiter, years during which scientists could only study the Voyager data and dream of the discoveries that a dedicated mission might make. During those intervening years, Europa remained a subject of fascination and speculation. The Voyager images were analysed and reanalyzed, yielding new insights even as they raised new questions. Theoretical models of Europa's interior were developed and refined, exploring the conditions under which a subsurface ocean might exist and remain liquid over geological time. The Moon became a touchstone for discussions of astrobiology and the search for life beyond Earth. And through it all, Europa continued its eternal orbit around Jupiter, circling the giant planet once every 3.5 days, its icy surface reflecting sunlight back toward the distant observers who had become so interested in its secrets. The Moon did not know it was being studied, did not care about the theories and debates it had inspired. It simply existed, a world unto itself waiting for the next visitors who would come to learn its story. As you rest now, let the images from Voyager settle into your imagination. Picture Europa as the spacecraft saw it, a pale sphere marked by dark lines and reddish stains, a world of ice hiding unknown depths. The linear features stretch across the surface like veins on a leaf, recording forces and processes that scientists are still working to understand. The smooth plains speak of geological youth, of a surface renewed again and again over millions of years. And beneath it all, perhaps, lies an ocean of liquid water, a hidden sea that has never seen sunlight but might nonetheless harbour life. The Voyager missions revealed Europa as one of the most intriguing worlds in our solar system. They showed us that this small moon, barely larger than our own moon, was far more complex and dynamic than anyone had imagined. They raised questions that would drive decades of subsequent research and exploration, and they planted seeds of wonder that continue to grow today as we plan new missions to study Europa and search for signs of life beneath its ice. The journey from Galileo's first telescopic observation to the Voyager flybys had taken nearly 4 centuries. In that time, Europa had transformed from a point of light to a world with known features and measurable properties. But the transformation was not complete. There was still so much to learn, so many mysteries to unravel. The Voyager encounters were a milestone, not a destination. Rest now in the knowledge that the universe continues to surprise us. that worlds we thought we understood can reveal unexpected wonders when we look more closely. Europa had surprised the Voyager scientists with its smooth surface and intricate fractures. It would surprise them again when the Galileo mission arrived, revealing new features and providing new evidence for the subsurface ocean that had been hypothesized. And it may surprise us still more in the years to come, as new missions probe its secrets and search for signs of life. The story of Europa is a story of discovery, of questions asked and gradually answered, of mysteries revealed and new mysteries uncovered. It is a story that connects the ancient myth of a princess carried across the sea to the modern quest to understand whether life might exist beyond Earth. And it is a story that is still being written, with new chapters unfolding as we continue to explore this remarkable moon. End of section 5. Word count, approximately 2,500 words. Running total, 13,950 words. Section 6. The Galileo mission, our deep dive. The Galileo mission represents one of the most ambitious and productive planetary exploration efforts ever undertaken. Named after the astronomer who first observed Jupiter's moons nearly 4 centuries earlier, this spacecraft would spend years studying the Jovian system in unprecedented detail, transforming our understanding of Jupiter and its satellites. For Europa in particular, Galileo would provide evidence that elevated the moon from an intriguing curiosity to one of the most promising places in the solar system to search for life. The origins of the Galileo mission trace back to the 1970s, when the success of the Pioneer and Voyager flybys demonstrated both the scientific value and technical feasibility of outer solar system exploration. Scientists and engineers began planning a more ambitious mission, one that would not simply fly past Jupiter but would enter orbit around the planet, allowing extended study of the entire Jovian system. The mission faced numerous challenges from the outset. The distance to Jupiter meant that the spacecraft would need to be highly autonomous, capable of operating for long periods without real-time control from Earth. The radiation environment near Jupiter required robust shielding to protect sensitive electronics, and the complexity of the mission, with its orbital insertion, multiple moon flybys, and atmospheric probe, demanded careful planning and sophisticated engineering. Budget constraints and shifting priorities delayed the mission repeatedly. Originally planned for launch in 1982, Galileo was pushed back several times as funding fluctuated and technical issues arose. The spacecraft was redesigned multiple times, with different launch vehicles and mission profiles considered. By the mid-1980s, Galileo was finally ready for launch, scheduled to ride into space aboard the Space Shuttle. Then came tragedy. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The disaster grounded the shuttle fleet for nearly 3 years as NASA investigated the cause and implemented safety improvements. Galileo, which had been scheduled to launch later that year, was forced to wait. When shuttle flights resumed, Galileo faced additional complications. The original mission plan had called for the spacecraft to be boosted toward Jupiter by a powerful Centaur upper stage carried in the shuttle's cargo bay. But safety concerns following the Challenger disaster led NASA to prohibit liquid-fueled upper stages on shuttle missions. Galileo would need to use a less powerful solid-fuel booster, which could not send the spacecraft directly to Jupiter. Engineers devised a creative solution. Instead of flying directly to Jupiter, Galileo would take a circuitous route, using gravity assists from Venus and Earth to gradually build up the speed needed to reach the outer solar system. This trajectory would add years to the journey, but it would allow the mission to proceed. Galileo finally launched on October 18, 1989, carried into orbit by the Space Shuttle Atlantis. the spacecraft deployed from the shuttle's cargo bay and fired its solid fuel booster, beginning a 6-year journey that would take it past Venus once and Earth twice before finally arriving at Jupiter in December 1995. The extended cruise phase was not wasted time. Galileo made observations of Venus during its flyby, studied the Earth-Moon system during its Earth encounters, and even flew past 2 asteroids, Gaspra and Ida, providing the first close-up images of these small rocky bodies. The Ida flyby yielded a particular surprise. The asteroid had a tiny moon of its own, the first confirmed satellite of an asteroid. But the cruise phase also brought problems. In April 1991, the spacecraft's high-gain antenna, a large umbrella-like structure designed to provide high-bandwidth communication with Earth, failed to deploy properly. Despite years of attempts to free the stuck antenna, it never opened fully. Galileo would have to rely on its low-gain antenna, which could transmit data at only a tiny fraction of the planned rate. This antenna failure had significant implications for the mission. Instead of the thousands of images originally planned, Galileo would be able to return only hundreds. Data would need to be carefully prioritized, with scientists forced to choose which observations were most important. The mission would still be scientifically valuable, but it would not achieve everything that had been hoped. Despite this setback, Galileo arrived at Jupiter on December 7, 1995, becoming the first spacecraft to enter orbit around an outer planet. On the same day, the atmospheric probe that Galileo had released 5 months earlier plunged into Jupiter's atmosphere, transmitting data for nearly an hour before being crushed and vaporized by the increasing pressure. The probe provided the first direct measurements of Jupiter's atmospheric composition and structure, revealing a world drier and more turbulent than expected. With the probe's mission complete, Galileo began its orbital tour of the Jovian system. Over the next 8 years, the spacecraft would complete 35 orbits of Jupiter, making close flybys of all 4 Galilean moons. Each orbit was carefully designed to bring the spacecraft close to one or more moons, allowing detailed observations that would have been impossible from greater distances. Europa was a primary target from the beginning. The Voyager images had revealed a world of unusual complexity, and scientists were eager to learn more. Galileo's first close flyby of Europa came in December 1996, when the spacecraft passed within about 700 kilometers of the Moon's surface. The images returned from this encounter were stunning, showing Europa's fractured surface in far greater detail than ever before. The linear features that Voyager had observed were revealed to be even more complex than previously thought. Some were double ridges, parallel raised structures separated by a central trough. Others were bands, regions where the ice appeared to have spread apart, and new material had filled the gap, similar to the spreading centres where new oceanic crust forms on Earth. Still others were chaotic terrain, regions where the surface had been disrupted and jumbled, with blocks of ice tilted and rotated as if floating on a liquid or soft substrate. The implications of these features were profound. The double ridges suggested that material from below the surface was being forced upward through cracks in the ice, building up raised structures on either side. The bands indicated that Europa's ice shell was being pulled apart by tectonic forces, with new ice forming to fill the gaps. And the chaotic terrain hinted that the ice shell might be relatively thin in some places, thin enough for underlying liquid or warm ice to disrupt and reorganize the surface. Galileo made 11 close flybys of Europa during its mission, each one providing new data and new insights. The spacecraft's camera captured images at resolutions as fine as a few meters per pixel, revealing details invisible to Voyager. Its spectrometer analyzed the composition of the surface, confirming the presence of water ice and detecting other compounds, including sulfuric acid and various salts. Its magnetometer measured the magnetic field around Europa, yielding what many consider the most compelling evidence for a subsurface ocean. The magnetic field measurements deserve special attention. Jupiter has an enormously powerful magnetic field, and as Europa orbits through this field, it experiences changing magnetic conditions. If Europa were simply a solid ball of rock and ice, it would not respond significantly to these changing conditions. But Galileo detected a secondary magnetic field around Europa, one that appeared to be induced by the changing Jovian field. An induced magnetic field of this type requires an electrically conductive layer near the surface. Rock and ice are poor conductors, but salt water conducts electricity quite well. The most straightforward explanation for the induced field was that Europa possessed a global layer of liquid salt water beneath its ice shell, a subsurface ocean that responded to Jupiter's changing magnetic field by generating its own induced field. This finding electrified the scientific community. The Voyager images had suggested the possibility of a subsurface ocean, but the magnetic field data provided much stronger evidence. Combined with the geological features that indicated ongoing or recent activity, the induced field made a compelling case that Europa harboured a liquid water ocean, potentially the largest ocean in the solar system. Galileo also provided data on Europa's interior structure. By tracking the spacecraft's radio signals as it flew past the Moon, scientists could measure tiny variations in its trajectory caused by Europa's gravitational field. These measurements revealed that Europa's interior was differentiated, with a dense core surrounded by a less dense outer layer. The data were consistent with a rocky core, possibly with an iron-rich inner core, surrounded by a shell of water in some form, either liquid, solid, or both. Combining the gravity data with the magnetic field measurements and the surface geology, scientists developed models of Europa's interior. The most widely accepted model features a metallic core, a rocky mantle, a liquid water ocean perhaps 100 kilometers deep, and an ice shell perhaps 10 to 30 kilometers thick. The exact dimensions remain uncertain, but the basic structure seems increasingly well established. The Galileo mission was extended multiple times, continuing long past its original planned duration. The spacecraft survived far longer than expected in Jupiter's harsh radiation environment, though the accumulated radiation damage eventually took its toll. By 2003, Galileo's systems were failing, and NASA faced a decision about how to end the mission. The concern was contamination. If Galileo was simply abandoned in orbit around Jupiter, it might eventually crash into one of the moons, potentially contaminating it with earthly microbes that might have survived aboard the spacecraft. Europa, with its possible subsurface ocean, was of particular concern. If life existed there, introducing terrestrial organisms could confuse future searches for native life, or even harm any existing ecosystem. To prevent this possibility, NASA deliberately crashed Galileo into Jupiter's atmosphere on September 21, 2003. The spacecraft that had revealed so much about the Jovian system was destroyed, vaporized in the crushing depths of the giant planet. It was a fitting end for a mission named after the astronomer who had first turned a telescope toward Jupiter, returning to the planet it had studied for so long. The legacy of the Galileo mission is immense. It transformed our understanding of Jupiter and its moons, revealing worlds far more complex and dynamic than anyone had imagined. For Europa specifically, Galileo provided evidence that elevated the Moon to the top tier of astrobiological targets, a place where the conditions for life might actually exist. The mission also raised as many questions as it answered. What is the exact thickness of Europa's ice shell? What is the composition of the ocean beneath? Are there hydrothermal vents on the ocean floor, similar to those that support ecosystems in Earth's deep oceans? Is there actually life in Europa's ocean, or is the moon a sterile world despite its habitable conditions? These questions could not be answered by Galileo. The spacecraft had done all it could with the instruments it carried and the time it had. Answering the remaining questions would require new missions, new instruments, and new approaches. The search for life on Europa, inspired and informed by Galileo's discoveries, would become a major focus of planetary science in the decades that followed. As you rest now, consider the journey that Galileo made. Launched from a space shuttle, delayed by tragedy, crippled by a stuck antenna, the spacecraft nonetheless achieved remarkable things. It revealed Europa as a world with a probable ocean, a place where life might conceivably exist. It showed us that the search for life need not be limited to planets orbiting in the habitable zones of stars, but might extend to moons warmed by tidal forces in the cold outer reaches of solar systems. The Galileo mission ended, but the exploration of Europa continues. New missions are being planned and built, carrying instruments far more sophisticated than anything Galileo possessed. The questions raised by Galileo's discoveries are being addressed by a new generation of scientists and engineers, people inspired by what the mission revealed and determined to learn more. Europa waits, as it has always waited, orbiting Jupiter in its eternal dance. Beneath its icy surface, an ocean may hold secrets we have not yet imagined. The story of Europa is far from over. Indeed, the most exciting chapters may still lie ahead. End of section 6. Word count, approximately 2,100 words running. Total, 15 to 250 words. Section 7. Europa's geology, a world like no other. To understand Europa is to understand ice, but not ice as we typically experience it on Earth. The ice that covers Europa exists under conditions vastly different from anything in our everyday experience, and it behaves in ways that might seem strange or counterintuitive. This ice shell, perhaps tens of kilometers thick, is not a static barrier, but a dynamic geological system, constantly shaped and reshaped by forces both internal and external. Understanding this ice and the features it creates is essential to understanding Europa as a world. The surface of Europa is composed primarily of water ice, but it is not pure. Spectroscopic observations from Galileo and ground-based telescopes have revealed the presence of various contaminants, including sulfuric acid, sulfur dioxide, and a variety of salts. These materials are not uniformly distributed, but are concentrated in certain areas, particularly along the linear features and in the chaotic terrain. Their presence suggests that material from beneath the surface has been brought up and deposited on the ice, providing clues about the composition of the subsurface ocean. The most prominent features on Europa's surface are the linear structures, the lines and ridges that crisscross the moon in intricate patterns. These features come in several varieties, each telling a different story about the processes that shaped them. Double ridges are perhaps the most common type of linear feature on Europa. These structures consist of two parallel raised ridges separated by a central trough or valley. They can extend for hundreds of kilometers across the surface, maintaining their parallel structure over vast distances. Some double ridges are relatively young, cutting across other features, while others are clearly older, disrupted or buried by subsequent geological activity. The formation of double ridges remains a subject of scientific debate, but the most widely accepted explanation involves the repeated opening and closing of cracks in the ice shell. As Europa orbits Jupiter, it experiences tidal forces that flex and deform its interior. These tidal forces cause the ice shell to crack, and as the cracks open, material from below, perhaps liquid water or warm ice, rises to fill the gap. When the cracks close again, this material is squeezed upward, building ridges on either side. Over many cycles of opening and closing, the ridges grow higher and the central trough deepens. If this explanation is correct, double ridges are evidence of ongoing or recent tidal activity on Europa. They suggest that the ice shell is not rigid and static, but is constantly being flexed and deformed by Jupiter's gravitational pull. And they imply that liquid water or warm ice exists not far beneath the surface, close enough to be mobilized when cracks open. Bands are another type of linear feature found on Europa. These are regions where the ice shell appears to have spread apart, with new material forming to fill the gap. The process is similar to seafloor spreading on Earth, where tectonic plates move apart at mid-ocean ridges and new oceanic crust forms from upwelling magma. On Europa, the spreading is driven not by plate tectonics in the terrestrial sense, but by the overall expansion and contraction of the ice shell due to tidal forces and possibly thermal effects. As the shell spreads apart in some areas, it must be compressed or subducted in others to maintain the overall surface area. Evidence for this compression and possible subduction has been found in some regions of Europa, though the details remain unclear. The bands on Europa often show distinctive patterns of light and dark material, with the dark material concentrated along the centre of the band where the spreading occurred. This dark material is thought to be contaminants brought up from below, perhaps salts or organic compounds from the subsurface ocean. The presence of this material provides additional evidence for a liquid or semi-liquid layer beneath the ice. Chaotic terrain, sometimes called chaos regions, represent some of the most dramatic and puzzling features on Europa. These are areas where the surface has been disrupted and jumbled, with blocks of ice tilted, rotated, and displaced from their original positions. The blocks often retain recognizable features from the surrounding terrain, allowing scientists to reconstruct their original positions like pieces of a jigsaw puzzle. The formation of chaotic terrain requires that the ice blocks be able to move independently, which implies that they were floating on something, either liquid water or warm, soft ice. This has led to suggestions that chaos regions form when the ice shell becomes thin enough for the underlying ocean or a subsurface lake to partially melt through, disrupting the surface before refreezing. One of the most studied chaos regions is Connemara Chaos, named after a region in Ireland. This area shows a particularly clear example of ice blocks that have been displaced and rotated, with dark matrix material filling the spaces between them. The dark material is thought to be oceanic material that welled up during the chaos formation event, providing a direct sample of what lies beneath the ice. The relative scarcity of impact craters on Europa is another important geological observation. On most airless bodies in the solar system, impact craters accumulate over time, providing a record of billions of years of bombardment. Europa's surface shows remarkably few craters, suggesting that the surface is geologically young, constantly renewed by processes that erase older features. Estimates of Europa's surface age, based on crater counts and models of the impact rate in the outer solar system, suggest that the average age is only about 40 to 90 million years. This is extraordinarily young in geological terms, implying that resurfacing processes are ongoing or were active until very recently. Whatever is renewing Europa's surface, whether cryovolcanism, tectonic activity, or some other process, it must be vigorous enough to erase craters faster than they accumulate. The few craters that do exist on Europa provide valuable information about the ice shell's properties. Some craters show unusual morphologies, with central peaks or multiple rings that differ from craters on rocky bodies. These differences reflect the behaviour of ice under impact conditions, which is different from the behaviour of rock. Some craters also show evidence of viscous relaxation, where the crater walls have slumped and the floor has risen over time, a process driven by the slow flow of ice under its own weight. This viscous relaxation occurs because of the warmth of the lower part of the ice shell. The strength of ice is very sensitive to temperature, and warm ice is soft and flows rather quickly, much like glaciers on Earth. Scientists have observed that the morphology and shape of craters on Europa change dramatically as crater diameters exceed approximately 30 kilometers. Craters smaller than 30 kilometers are several hundred meters deep and have recognizable rims and central uplifts, which are standard features of impact craters. But larger craters behave differently, their shapes modified by the unusual properties of Europa's ice shell. The presence of central peaks within some European craters suggests that impacts did not melt through the entire ice shell, implying that the ice shell is at least 3 to 4 kilometers thick. Studies of craters approximately 10 to 18 kilometers in diameter, which would have excavated material from depths of 3 to 6 kilometers, concluded that these impacts did not penetrate down to a liquid layer. Therefore, the ice shell of Europa must be at least 6 kilometers thick. The largest impact structures on Europa are surrounded by concentric rings and appear to be filled with relatively flat, fresh ice. Based on this observation and on calculations of the amount of heat generated by European tides, scientists estimate that the outer crust of solid ice is approximately 10 to 30 kilometers thick, including a ductile warm ice layer. This could mean that the liquid ocean underneath may be about 100 kilometers deep, a staggering volume of water that exceeds all the oceans of Earth combined. Two of the most studied large impact features on Europa are Callanish and Tyre. These structures do not appear to be simply larger and more viscously relaxed versions of classic craters. Rather, they display totally different morphologies, such as distinctive textures and a series of large concentric structural rings cutting through impact-related materials. These multi-ring basins provide crucial constraints on Europa's ice shell thickness, as the formation of such structures depends on the mechanical properties of the ice and the presence of underlying liquid. When an impact crater forms, it essentially probes the subsurface structure of a planetary body. By understanding the sizes and shapes of craters on Europa and reproducing their formation with numerical simulations, scientists are able to infer information about how thick the ice shell is. Compared to craters on Ganymede and Callisto, European craters transition to anomalously shallow depths and anomalous morphologies at smaller diameters. This trend is linked to the presence of an underlying global ocean at depths of a few tens of kilometers. The study of crater morphology has revealed three distinct transitions on Europa. The first is the simple to complex transition, where craters develop central peaks and terraced walls. The second involves anomalous crater dimensions and morphologies, including central pits and domes, with crater depths that decrease as crater diameter increases. The third is an abrupt transition from modified central peak craters to shallow craters with multi-ring morphologies. Each of these transitions tells us something about the structure beneath the surface, about the layers of cold, brittle ice, warm, ductile ice, and liquid water that make up Europa's outer shell. The pedestal ejecta facies observed around some European craters may be produced by the relief-flattening movement of plastically deforming but otherwise solid ice that was warm at the time of emplacement. This suggests that even the solid portions of Europa's ice shell are not entirely rigid, but can flow and deform under the right conditions, contributing to the overall geological activity of the Moon. Beyond craters, Europa's surface displays a remarkable variety of other geological features. Lenticulae, small rounded features typically about 10 kilometers in diameter, dot the surface in many regions. These features appear to be places where warm ice or liquid water has risen from below, doming up the surface before either breaking through or refreezing. Some lenticulae are simple domes, while others have collapsed into pits, and still others have disrupted the surrounding terrain to form small chaos regions. The distribution of lenticulae across Europa's surface is not random. They tend to cluster in certain areas, suggesting that the conditions necessary for their formation, perhaps thin ice or concentrated heat flow, are not uniform across the Moon. Understanding this distribution could provide clues about the structure of the ice shell and the patterns of heat flow from the interior. Cycloids are another distinctive feature found on Europa. These are chains of arc-shaped segments that curve across the surface, each arc connected to the next at a cusp. The shape of cycloids is thought to result from the way cracks propagate through the ice as Europa experiences tidal stresses during its orbit around Jupiter. As the tidal forces change direction, the crack changes direction as well, creating the characteristic curved segments. The presence of cycloids is strong evidence that tidal forces are actively shaping Europa's surface. The patterns of these features can be used to reconstruct the stress history of the ice shell, providing information about how the tidal forces vary across the surface and over time. Some cycloids appear to be relatively young, cutting across other features, while others are clearly older, partially buried or disrupted by subsequent activity. Ridges of various types cover much of Europa's surface. In addition to the double ridges discussed earlier, there are single ridges, ridge complexes, and ridge-dominated plains, where ridges are so numerous that they form the primary texture of the landscape. The variety of ridge types suggests that multiple formation mechanisms may be at work, or that a single mechanism can produce different results depending on local conditions. Some ridges appear to be purely tectonic features, formed by compression or extension of the ice shell. Others may have a cryovolcanic component, with material erupted along the ridge crest contributing to its height. Still others may form through a combination of processes, with tectonic cracking followed by infilling and subsequent deformation. Sorting out these different possibilities requires detailed analysis of individual features, comparing their morphology, composition, and relationship to surrounding terrain. The overall impression of Europa's geology is one of constant activity and change. Unlike the ancient, heavily cratered surfaces of many solar system bodies, Europa's surface is young and dynamic. The ice shell is not a passive barrier between the surface and the ocean below, but an active geological system, shaped by tidal forces, heat flow, and the movement of material between the surface and the interior. This geological activity has important implications for the possibility of life on Europa. If material from the ocean can reach the surface, then material from the surface can presumably reach the ocean as well. Oxidants produced by radiation at the surface, compounds that could serve as energy sources for life, might be transported downward through the ice shell to the ocean below. This cycling of material between surface and ocean could provide the chemical energy needed to sustain a biosphere, even in the absence of sunlight. The geology of Europa also presents challenges for future exploration. The fractured, ridge terrain would be difficult to navigate for any surface mission. The ice shell, while providing access to the ocean below, is also a barrier that must be penetrated to reach that ocean. Understanding the structure and properties of the ice shell is essential for planning missions that might one day drill through it to sample the waters beneath. As you rest now, let the complex geology of Europa settle into your imagination. Picture the double ridges stretching across the icy plains, the chaotic terrain where ice blocks have been jumbled and rotated, the smooth floors of impact craters that have relaxed over millions of years. This is a world shaped by forces we are only beginning to understand, a world where ice behaves in ways that challenge our intuitions and expand our knowledge. The geology of Europa is a window into the moon's interior, a record of processes that operate beneath the surface we can see. Every ridge, every band, every chaos region tells a story about the forces that shaped it, about the ice shell and the ocean below. Reading these stories is the work of planetary geologists, scientists who study the surfaces of other worlds to understand what lies beneath. And beneath Europa's surface lies an ocean, a vast body of liquid water that may be the largest ocean in the solar system. In the next section, we will dive into that ocean, exploring what we know and what we suspect about this hidden realm. The geology we have discussed is just the surface expression of a world that extends far deeper, into darkness and mystery, and perhaps into life. End of section 7. Word count, approximately 300 words. Running total, late 350 words. Section 8. The subsurface ocean, hidden depths. Beneath the fractured ice of Europa lies what may be the most significant body of water in our solar system beyond Earth. This subsurface ocean, hidden from direct observation, but revealed through multiple lines of evidence, has transformed Europa from a mere moon into one of the most compelling targets in the search for life beyond our planet. To understand Europa fully, we must venture beneath the ice, into the darkness where sunlight never penetrates, where pressures are immense and where conditions might just be right for life to exist. The evidence for Europa's ocean comes from several independent sources, each contributing a piece to the puzzle. We have already discussed the geological evidence, the young surface features that suggest ongoing activity driven by liquid water or warm ice beneath the shell. We have mentioned the magnetic field measurements from Galileo, which detected an induced field consistent with a global layer of electrically conducting fluid. But there is more to the story, additional evidence that strengthens the case for a subsurface ocean. The density of Europa, determined from tracking the gravitational effects on passing spacecraft, tells us about the moon's bulk composition. Europa's average density is about 3.01 grams per cubic centimetre, significantly higher than the icy moons of Saturn, but lower than purely rocky bodies like our moon. This density is consistent with a body composed primarily of rock, with a substantial outer layer of water in some form. The water layer, whether liquid, solid, or both, must constitute a significant fraction of Europa's volume. Thermal models of Europa's interior provide additional support for a liquid ocean. Europa experiences tidal heating as it orbits Jupiter, its interior flexed and deformed by the giant planet's gravitational pull. This tidal heating generates warmth within the moon, warmth that must go somewhere. If Europa's interior were entirely solid, the heat would conduct slowly outward through the ice, eventually radiating into space. But the amount of tidal heating predicted by models is sufficient to maintain a liquid layer beneath the ice, preventing the ocean from freezing solid. The orbital resonance between Europa, Io, and Ganymede plays a crucial role in this tidal heating. Because the three moons are locked in a gravitational dance, with their orbital periods in a precise ratio, Europa's orbit is forced to be slightly elliptical rather than perfectly circular. This ellipticity means that Europa's distance from Jupiter varies over the course of each orbit, and so does the strength of the tidal forces it experiences. The constant flexing as these forces wax and wane generates heat through friction within the moon's interior. The amount of heat generated by tidal flexing depends on several factors, including the eccentricity of Europa's orbit, the rigidity of its interior, and the efficiency with which mechanical energy is converted to heat. Estimates vary, but most models suggest that tidal heating produces somewhere between 10 and 100 times more heat than radioactive decay in Europa's rocky core. This is more than enough to maintain a liquid ocean beneath an ice shell of reasonable thickness. The thickness of the ice shell remains one of the most debated questions about Europa. Estimates range from just a few kilometres to more than 30 kilometres, with different lines of evidence pointing to different values. The geological features we discussed earlier, particularly the chaos terrain and lenticular, seem to require relatively thin ice, perhaps less than 10 kilometres, to allow warm material from below to disrupt the surface. But the large impact craters and their relaxation pattern suggest thicker ice, perhaps 20 kilometres or more. One possibility is that the ice shell thickness varies across Europa's surface. The tidal heating is not uniform, but concentrated in certain regions, particularly near the equator and at certain longitudes. Where heating is strongest, the ice might be thinner, allowing more surface disruption. Where heating is weaker, the ice might be thicker and more stable. This variation could explain why some regions of Europa show abundant chaos terrain and lenticular, while others are dominated by older, more stable ridged plains. Another possibility is that the ice shell has two distinct layers, a cold, brittle outer layer and a warm, ductile inner layer. The cold outer layer would behave rigidly, cracking and fracturing under tidal stress. The warm inner layer would flow more easily, convecting heat from the ocean below and potentially allowing material to rise toward the surface. The boundary between these layers might be gradual rather than sharp, with ice transitioning from brittle to ductile as temperature increases with depth. If a liquid ocean exists beneath Europa's ice, how deep might it be? The answer depends on the thickness of the ice shell and the total amount of water on Europa. Based on the Moon's density and size, scientists estimate that the water layer, including both ice and liquid, is roughly 80 to 170 kilometres thick. If the ice shell is 20 kilometres thick, the ocean beneath could be 60 to 150 kilometres deep. This is far deeper than any ocean on Earth, where the average depth is only about 3.7 kilometres, and the deepest point in the Mariana Trench reaches only about 11 kilometres. The volume of water in Europa's ocean, if it exists, would be enormous. Estimates suggest that Europa contains 2 to 3 times as much water as all of Earth's oceans combined. This vast reservoir of liquid water, maintained by tidal heating over billions of years, represents one of the largest potentially habitable environments in our solar system. But what would conditions be like in this ocean? The pressure at the bottom would be immense, hundreds of times greater than the pressure at the bottom of Earth's deepest trenches. The temperature would likely be near freezing at the top, where the ocean meets the ice shell, but could be warmer at greater depths, particularly if there are hydrothermal vents on the ocean floor. The composition of Europa's ocean is another important question. On Earth, seawater is salty, containing about 3.5% dissolved salts by weight, primarily sodium chloride. Europa's ocean is also likely to be salty, based on the spectroscopic detection of salts on the surface and the need for electrical conductivity to explain the induced magnetic field. But the specific salts present and their concentrations remain uncertain. Some models suggest that Europa's ocean might be similar in salinity to Earth's oceans, while others propose that it could be much saltier, perhaps approaching the salinity of the Dead Sea or even higher. The salinity would affect the ocean's freezing point, its density, and its ability to support life. Very high salinity could make the ocean inhospitable to life as we know it, while moderate salinity might be compatible with a wide range of organisms. The pH of the ocean, its acidity or alkalinity, is another unknown. On Earth, seawater is slightly alkaline, with a pH around 8.1. Europa's ocean could be similar, or it could be more acidic or more alkaline depending on the chemical reactions occurring between the water and the rocky seafloor. The pH would affect which chemical reactions are possible and which types of life might be able to survive. One of the most intriguing possibilities is that Europa's ocean floor might host hydrothermal vents, similar to those found in Earth's deep oceans. On Earth, hydrothermal vents occur where seawater seeps into cracks in the oceanic crust, is heated by underlying magma, and then rises back to the seafloor, carrying dissolved minerals and chemicals. These vents support thriving ecosystems, communities of organisms that derive their energy not from sunlight, but from chemical reactions between the vent fluids and seawater. If similar vents exist on Europa, they could provide both the chemical energy and the nutrients needed to support life. The interaction between hot, mineral-rich water and the cold ocean could drive chemical reactions that produce compounds usable by living organisms. Bacteria and archaea on Earth thrive in such environments, and similar organisms might conceivably exist on Europa. The rocky seafloor of Europa is another important factor. Unlike some icy moons, which may have oceans sandwiched between layers of ice, Europa's ocean is thought to be in direct contact with a rocky mantle. This contact allows for chemical exchange between the rock and the water, potentially enriching the ocean with minerals and elements essential for life. On Earth, the interaction between seawater and oceanic crust is a major driver of ocean chemistry, and similar processes could operate on Europa. The possibility of volcanism on Europa's seafloor adds another dimension to this picture. If the rocky interior is geologically active, volcanic eruptions could release gases and minerals into the ocean, providing additional chemical energy and nutrients. The tidal heating that warms Europa's interior might also drive volcanic activity in the rocky mantle, creating a dynamic environment at the ocean floor. Recent observations have added new evidence to the case for Europa's ocean. The Hubble Space Telescope has detected what appear to be plumes of water vapour erupting from Europa's surface, similar to the geysers observed on Saturn's moon Enceladus. If confirmed, these plumes would provide direct evidence that liquid water exists beneath the ice and occasionally breaks through to the surface. The plumes were first reported in 2012 based on ultraviolet observations that showed excess hydrogen and oxygen near Europa's south pole. Subsequent observations have provided additional evidence, though the plumes appear to be intermittent, not always visible when Europa is observed. The sporadic nature of the plumes suggests that they might be triggered by tidal stresses, erupting when cracks in the ice open during certain parts of Europa's orbit. If plumes are indeed erupting from Europa, they offer an exciting opportunity for future exploration. A spacecraft flying through a plume could sample the material directly, analysing its composition without needing to land on the surface or drill through the ice. This could provide direct information about the ocean's chemistry, including whether it contains organic molecules or other signs of potential habitability. The subsurface ocean of Europa represents one of the most tantalizing environments in our solar system. It is a place of darkness and pressure, of cold water and rocky depths, of chemical reactions and energy flows that we are only beginning to understand. Whether life exists there remains unknown, but the conditions seem promising, more promising than anywhere else we have found beyond Earth. As you rest now, let your imagination sink beneath Europa's ice, into the darkness of the ocean below. Picture the water stretching downward for tens of kilometres, cold and black and silent. Picture the seafloor far below, rocky and perhaps volcanic, perhaps dotted with hydrothermal vents that glow with chemical heat. Picture the possibility, however remote, that something lives in that darkness, something that has never seen the sun, something that draws its energy from the chemistry of water and rock. The ocean of Europa is hidden from our view, but it is not beyond our reach. Future missions will probe this hidden realm, searching for signs of life and seeking to understand the processes that operate in this alien environment. The story of Europa's ocean is still being written, and the most exciting chapters may lie ahead. End of Section 8. Word count, approximately 1,950 words running. Total, 2,300 words. Section 9. Astrobiology, the search for life. The question of whether life exists beyond Earth is one of the most profound questions humanity has ever asked. For centuries, this question was the province of philosophers and theologians, a matter of speculation rather than scientific inquiry. But in recent decades, the search for extraterrestrial life has become a rigorous scientific endeavour, guided by our understanding of biology, chemistry, and planetary science. And Europa has emerged as one of the most promising places to look. What makes Europa such a compelling target for astrobiology? The answer lies in the requirements for life as we understand it. Based on our knowledge of life on Earth, the only example we have, certain conditions appear to be necessary for life to exist. These include liquid water, a source of energy, and the chemical building blocks from which living organisms are constructed. Europa appears to possess all three. Liquid water is perhaps the most fundamental requirement. All life on Earth depends on water, which serves as the medium in which biochemical reactions occur. Water's unique properties, its ability to dissolve a wide range of substances, its role in temperature regulation, its participation in countless chemical reactions, make it essential for life as we know it. Europa's subsurface ocean provides a vast reservoir of liquid water, potentially the largest in the solar system. Energy is the second requirement. Life needs energy to drive the chemical reactions that sustain it, to build complex molecules, to grow and reproduce. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly by consuming organisms that photosynthesize. But Europa's ocean is cut off from sunlight by kilometers of ice. Any life there would need to rely on alternative energy sources. Fortunately, alternative energy sources exist. On Earth, entire ecosystems thrive in the deep ocean, far from sunlight, sustained by chemical energy from hydrothermal vents. These chemosynthetic ecosystems use the energy released by chemical reactions, such as the oxidation of hydrogen sulfide or methane, to produce organic matter. Similar processes could operate on Europa, providing energy for life in the absence of sunlight. The chemical building blocks of life are the third requirement. Life on Earth is based on carbon, which forms the backbone of organic molecules. Other elements, including hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are also essential. These elements must be available in forms that can be incorporated into biological molecules. Europa's ocean, in contact with a rocky seafloor, could be enriched with these elements through chemical weathering and hydrothermal activity. The combination of liquid water, chemical energy, and essential elements makes Europa one of the most promising environments for life in our solar system. But promising does not mean certain. We do not know whether life actually exists on Europa, and we will not know until we can investigate more directly. The search for life on Europa faces significant challenges. The ocean is hidden beneath kilometers of ice, inaccessible to direct observation. The surface is bathed in intense radiation from Jupiter's magnetosphere, which would destroy any organic molecules exposed there. And the distances involved make exploration difficult and expensive, requiring years of travel time and sophisticated technology. Despite these challenges, scientists have developed strategies for searching for life on Europa. One approach is to look for biosignatures, chemical or physical signs that would indicate the presence of life. On Earth, life produces distinctive chemical signatures, such as the oxygen in our atmosphere, which is maintained by photosynthesis, or the specific ratios of carbon isotopes in organic matter. Similar signatures might be detectable on Europa if life exists there. The possible plumes erupting from Europa's surface offer a particularly exciting opportunity. If spacecraft can fly through these plumes and sample the material, they could analyze it for organic molecules, chemical disequilibria, or other potential biosignatures. This approach has already been used at Enceladus, where the Cassini spacecraft flew through plumes erupting from that moon and detected organic molecules and other intriguing compounds. Another approach is to study Europa's surface for signs of material from the ocean below. The geological features we discussed earlier, particularly the chaos terrain and the dark material along ridges and bands, may contain oceanic material that has been brought to the surface. Analysing this material could provide information about the ocean's composition and potential habitability. The radiation environment at Europa's surface complicates this approach. The intense radiation breaks apart molecules, altering their chemistry and potentially destroying biosignatures. Any organic molecules brought to the surface would be degraded over time, making detection more difficult. However, material buried just below the surface might be protected from radiation, preserved in a more pristine state. Future missions to Europa will carry instruments designed to search for signs of life. These include mass spectrometers that can identify organic molecules, spectrometers that can analyze surface composition, and cameras that can image the surface at high resolution. Some proposed missions would land on Europa's surface, allowing direct sampling of the ice. Others would orbit the moon, making repeated passes to build up a comprehensive picture of its properties. The most ambitious proposals envision missions that would penetrate Europa's ice shell to reach the ocean below. These concepts include cryobots, heated probes that would melt their way through the ice, and submarines that would explore the ocean once the ice was breached. Such missions are technically challenging and expensive, but they represent the most direct way to search for life in Europa's ocean. While we wait for these future missions, scientists continue to study life in extreme environments on Earth, seeking insights that might apply to Europa. The field of extremophile biology has revealed that life can thrive in conditions once thought impossible, from boiling hot springs to frozen Antarctic lakes, from highly acidic mine drainage to the crushing pressures of the deep ocean. Particularly relevant are the ecosystems around deep-sea hydrothermal vents. These communities exist in complete darkness, sustained by chemical energy rather than sunlight. The base of the food chain consists of chemosynthetic bacteria and archaea, microorganisms that derive energy from chemical reactions between vent fluids and seawater. These microbes support a diverse community of larger organisms, including tube worms, clams, shrimp, and fish. The discovery of hydrothermal vent ecosystems in the late 1970s revolutionized our understanding of where life can exist. Before this discovery, it was assumed that all life ultimately depended on sunlight. The vent communities showed that life could thrive in the absence of light, sustained by the chemical energy of the Earth itself. This finding has profound implications for the search for life on Europa and other ocean worlds. Another relevant environment is the subglacial lakes of Antarctica, bodies of liquid water that exist beneath kilometers of ice. The most famous of these is Lake Vostok, a lake roughly the size of Lake Ontario that lies beneath nearly 4 kilometers of ice. Despite the extreme conditions, microbial life has been found in water samples from subglacial lakes, demonstrating that life can persist in cold, dark, isolated environments. The study of these extreme environments informs our expectations for Europa. If life exists there, it is likely to be microbial, consisting of simple single-celled organisms rather than complex multicellular life. These microbes might be chemosynthetic, deriving energy from chemical reactions rather than light. They might live in the water column, on the seafloor, or within the ice shell itself, wherever conditions allow. The possibility of life on Europa raises important ethical and practical questions. If we discover life there, how should we respond? What precautions should we take to avoid contaminating Europa with earthly organisms, which could confuse our search for native life, or even harm any existing ecosystem? These questions of planetary protection are taken seriously by space agencies, which implement strict protocols to minimize the risk of contamination. The Galileo spacecraft, as we discussed earlier, was deliberately crashed into Jupiter at the end of its mission to prevent any possibility of it contaminating Europa. Future missions will face similar considerations, balancing the desire for close investigation against the need to protect any potential biosphere. The search for life on Europa is not just a scientific endeavour, but a philosophical one. The discovery of life beyond Earth, even microbial life, would be one of the most significant findings in human history. It would tell us that life is not unique to our planet, that the processes that gave rise to life on Earth can occur elsewhere. It would transform our understanding of our place in the universe. Even if we do not find life on Europa, the search itself is valuable. Understanding the conditions on Europa, the chemistry of its ocean, the processes that shape its surface, expands our knowledge of planetary science and astrobiology. It helps us understand the range of environments where life might exist, informing the search for life elsewhere in the universe. As you rest now, consider the possibility that we are not alone. Somewhere beneath the ice of Europa, in the darkness of an alien ocean, life might exist. It would be life unlike anything we know, adapted to conditions we can barely imagine. But it would be life nonetheless, a second example of the phenomenon that makes our own existence possible. The search for life on Europa continues. New missions are being planned, new instruments developed, new strategies devised. The question of whether life exists there remains open, waiting for the evidence that will allow us to answer it. And in that waiting, there is wonder. The wonder of not knowing, the wonder of possibility, the wonder of a universe that may be far more alive than we ever imagined. End of section 9. Word count, approximately 1,700 words running. Total, 22,000 words. Section 10. Europa in the Jovian system. Europa does not exist in isolation. It is part of a complex system, a family of moons orbiting the largest planet in our solar system. To fully understand Europa, we must consider its context, the gravitational forces that shape it, the radiation that bathes it, and the relationships it has with its sibling moons. The Jovian system is a miniature solar system in its own right, and Europa's place within it determines much of what makes the moon so remarkable. Jupiter dominates its system in every way. The planet is more massive than all other objects in the solar system combined, excluding the Sun. Its gravitational influence extends millions of kilometers into space, capturing moons, deflecting asteroids, and shaping the orbits of everything nearby. Jupiter's magnetic field, the strongest of any planet, creates a vast magnetosphere that engulfs its inner moons in a cocoon of charged particles and radiation. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are the largest members of Jupiter's satellite family. They range in size from Europa, the smallest of the 4 at about 1,100 kilometers in diameter, to Ganymede, the largest moon in the solar system at about 5,068 kilometers in diameter. Each of these moons is a world in its own right, with distinctive characteristics and geological histories. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Its surface is constantly renewed by volcanic eruptions, with lava flows, volcanic plumes, and sulfurous deposits covering the landscape. Io's volcanism is driven by intense tidal heating, the result of its close proximity to Jupiter and its orbital resonance with Europa and Ganymede. The same forces that heat Io also heat Europa, though to a lesser degree. Ganymede, the largest moon, is a world of ice and rock, with a surface that shows evidence of past geological activity. Grooved terrain, where the surface has been deformed and reshaped, alternates with older, heavily cratered regions. Ganymede is the only moon in the solar system known to have its own magnetic field, generated by a liquid iron core. Like Europa, Ganymede may possess a subsurface ocean, though the evidence is less compelling. Callisto, the outermost Galilean moon, presents a stark contrast to its siblings. Its surface is ancient and heavily cratered, showing little evidence of geological activity. Callisto appears to be a frozen dead world, its interior never having experienced the tidal heating that shaped Io, Europa, and Ganymede. Yet even Callisto may harbour a subsurface ocean, maintained not by tidal heating but by the slow decay of radioactive elements in its interior. The orbital resonance between Io, Europa, and Ganymede is one of the most important features of the Jovian system. This resonance, called the Laplace resonance after the mathematician who first analysed it, locks the three moons into a precise orbital relationship. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This relationship has persisted for billions of years, maintained by the gravitational interactions between the moons. The Laplace resonance has profound consequences for all 3 moons involved. It forces their orbits to be slightly elliptical rather than perfectly circular, which means that the tidal forces they experience vary over the course of each orbit. This variation causes the moon's interiors to flex and deform, generating heat through friction. The amount of heating depends on the moon's distance from Jupiter and the eccentricity of its orbit, with Io experiencing the most heating and Ganymede the least. For Europa, the tidal heating generated by the Laplace resonance is thought to be the primary source of internal heat, the energy that maintains the subsurface ocean and drives geological activity. Without this resonance, Europa's orbit would be more circular, tidal heating would be reduced, and the ocean might freeze solid. The resonance is thus essential to Europa's potential habitability. The radiation environment near Jupiter is another important factor in Europa's story. Jupiter's powerful magnetic field traps charged particles from the solar wind and from volcanic emissions from Io, creating intense radiation belts that extend throughout the inner Jovian system. Europa orbits within these radiation belts, its surface constantly bombarded by high-energy electrons and ions. This radiation has both destructive and creative effects. On the destructive side, it damages organic molecules, breaks apart chemical compounds, and poses hazards for spacecraft electronics. Any life on Europa's surface would be quickly destroyed by the radiation, which is why the search for life focuses on the subsurface ocean, protected by kilometers of ice. On the creative side, the radiation drives chemical reactions that might be important for life. When high-energy particles strike Europa's icy surface, they break apart water molecules, creating reactive compounds like hydrogen peroxide and oxygen. These oxidants could potentially be transported through the ice shell to the ocean below, where they might serve as energy sources for chemosynthetic life. The radiation that makes Europa's surface hostile might thus contribute to making its ocean habitable. Europa's thin atmosphere, Technically, an exosphere is another product of the radiation environment. The bombardment of the surface releases water molecules and other compounds into space, creating a tenuous envelope of gas around the Moon. This exosphere is constantly being lost to space and replenished from the surface, a dynamic balance maintained by the ongoing radiation bombardment. The interaction between Europa and Jupiter's magnetic field produces interesting effects. As Europa moves through the magnetosphere, it creates disturbances in the magnetic field, generating electrical currents and inducing the secondary magnetic field that provided evidence for the subsurface ocean. This interaction also produces auroras, glowing regions where charged particles strike the atmosphere and excite gas molecules to emit light. Europa's relationship with its sibling moons extends beyond the orbital resonance. Material ejected from Io's volcanoes spreads throughout the Jovian system, creating a torus of plasma that encircles Jupiter. Some of this material reaches Europa, depositing sulfur and other volcanic compounds on its surface. The reddish-brown discoloration seen on Europa may be partly due to this sulfur contamination, though other sources, including material from the subsurface ocean, likely contribute as well. The comparative study of the Galilean moons provides insights into planetary evolution and the conditions necessary for habitability. Io, Europa, Ganymede and Callisto form from the same disk of material that surrounded Jupiter early in the solar system's history, yet they have evolved into very different worlds. Understanding why requires considering their different distances from Jupiter, their different compositions, and the complex gravitational interactions between them. Io's extreme volcanism results from its close proximity to Jupiter and the intense tidal heating this produces. The periodic alignment of Io, Europa, and Ganymede results in forced eccentric orbits, so the shapes of these moons periodically change as they orbit massive Jupiter, with the most intense deformation and heating occurring at innermost Io. Europa's potential habitability results from a more moderate level of tidal heating, enough to maintain a liquid ocean, but not so much as to drive the extreme volcanism seen on Io. Between these hot and cold extremes, Europa orbits at a distance where Jupiter's tidal heating may be just right to sustain a liquid water ocean beneath its icy crust. Ganymede and Callisto, farther from Jupiter, experience progressively less tidal heating, resulting in less geological activity, and in Callisto's case, an ancient surface that has changed little over billions of years. This gradient of tidal heating across the Galilean moons creates a natural laboratory for studying how internal heat affects planetary evolution. Io represents one extreme, where tidal heating is so intense that the moon's interior is largely molten, driving continuous volcanic activity that resurfaces the entire moon every few thousand years. Callisto represents the other extreme, where tidal heating is negligible and the moon has remained geologically dormant for most of its history. Europa and Ganymede fall between these extremes, with enough internal heat to drive geological processes, but not so much as to create the volcanic chaos seen on Io. The tidal heating effect warms Europa's interior, which keeps the interior water in a liquid state. As Europa moves slightly away from Jupiter during its elliptical orbit, Jupiter's gravitational force decreases, causing Europa to relax back into a more spherical shape and creating tides in its ocean. The orbital eccentricity of Europa is continuously pumped by its mean motion resonance with Io, ensuring that this tidal flexing continues indefinitely. Thus, the tidal flexing needs Europa's interior and gives it a source of heat, possibly allowing its ocean to stay liquid while driving subsurface geological processes. Understanding tidal heating requires appreciating the mechanics of how gravitational forces translate into internal heat. As the outer portions of moons like Io and Europa flex up and down in response to tides, the friction of rock and ice grains sliding across each other releases heat. On Io, this heating produces volcanic activity that is far more active and intense than volcanism on Earth. On Europa, the tidal heating may have heated its interior enough to melt ice and produce a subsurface ocean. The difference lies in the intensity of the heating and the composition of the moon, with Io's rocky interior responding differently than Europa's icy shell. Most planetary scientists were staggered to find active volcanoes on Io when Voyager 1 arrived at Jupiter, but not the authors of a paper that had been published in the journal Science just a few days before the encounter. In this paper, Stanton Peele and colleagues proposed that Io's interior should be largely molten because of heat generated by the tidal stressing experienced by Io as it orbits Jupiter. This prediction, confirmed so dramatically by Voyager's images of volcanic plumes, demonstrated the power of theoretical understanding to anticipate discoveries before they are made. We now know that Io is home to over 400 active volcanoes, making it the most geologically active body in the solar system. The gravitational forces involved stretch and squeeze not just Io, but also Europa, Ganymede, and Callisto, all of them interesting because of the possibility of liquid oceans beneath the surface. Io is close enough to Jupiter that rock can be melted into magma, but it is the ice under more distant Europa that gets the lion's share of interest because of its astrobiological possibilities. Although there is general agreement that the cause of Io's heat is tidal heating from the pull of gravity from Jupiter and its moon Europa, the volcanoes are not in the positions predicted with tidal heating alone. They are shifted 30 to 60 degrees to the east, a puzzle that scientists have worked to explain. A study published by the Astrophysical Journal in 2015 explains the eastern shift by an ocean of molten rock under the surface, where the movement of this magma would generate extra heat. This finding suggests that Io's interior is even more complex than simple tidal heating models would predict, with a global magma ocean influencing the distribution of volcanic activity. Io has been volcanically active for billions of years, according to recent research. Scientists use Io as a laboratory for understanding tidal heating in general, since it represents the most extreme example of this phenomenon in our solar system. Sophisticated modelling of Io's sulfur system has explored potential scenarios for the Moon's history, including some in which Io was even more volcanically active in the past than it is today. Understanding Io's long volcanic history helps scientists understand how tidal heating has evolved over time and how it might have affected Europa's ocean throughout the solar system's history. Meanwhile, tidal heating of Europa and of Saturn's moon Enceladus maintains subsurface oceans that are below relatively thin ice shells and in contact with the moon's silicate cores, providing key ingredients for habitability. This contact between liquid water and rock is crucial for astrobiology, as it allows for chemical reactions that could provide energy and nutrients for life. The comparison between Europa and Enceladus has become an important theme in planetary science, as both moons offer opportunities to study ocean worlds and search for signs of life. If Io's eccentricity were all natural eccentricity, a happy medium would be reached, with Io rotating on a synchronous, near-circular orbit, with a tidal bulge of roughly consistent size and shape pointing towards Jupiter. This is what has happened with the Earth-Moon system, where the tidal distortion stays roughly the same, and not much heat is dissipated. However, Io's eccentricity is being ramped up by the proximity of its neighbouring satellites, particularly Europa and Ganymede. This forced eccentricity is the key to understanding why tidal heating persists on Io and Europa, rather than dying away as the moons' orbits circularize. The relationship between the Galilean moons extends beyond gravitational interactions. Material ejected from Io's volcanoes spreads throughout the Jovian system, creating a plasma torus that encircles Jupiter. This volcanic material, rich in sulfur and other compounds, interacts with the other moons as they orbit through it. Some of this material reaches Europa, potentially contributing to the reddish-brown discoloration observed on its surface. Jupiter's magnetic field plays a crucial role in distributing Io's volcanic output throughout the system. Charged particles from Io are trapped by the magnetic field and accelerated to high energies, contributing to the intense radiation environment that bathes the inner moons. This radiation, while hazardous, also drives chemical reactions on Europa's surface that might be important for habitability. The study of the Jovian system as an integrated whole has become increasingly important in planetary science. Rather than viewing each moon in isolation, scientists now recognize that the moons interact with each other and with Jupiter in complex ways. The orbital resonances, the tidal heating, the radiation environment, and the exchange of material between moons all contribute to making the Jovian system a dynamic and interconnected place. For Europa specifically, its position within this system is crucial to its potential habitability. Too close to Jupiter, and it would be like Io, a volcanic hellscape where any water would be vaporized. Too far, and it would be like Callisto, a frozen world where any ocean would have long since frozen solid. Europa occupies a sweet spot, a Goldilocks zone within the Jovian system, where conditions are just right for liquid water to persist beneath an icy shell. This concept of a Goldilocks zone within a planetary system, distinct from the traditional habitable zone around a star, has important implications for the search for life in the universe. It suggests that habitable environments might exist far from stars, in the outer reaches of planetary systems, where tidal heating from giant planets can maintain liquid water. Moons like Europa expand the potential real estate for life in the cosmos, suggesting that habitable worlds might be far more common than we once thought. The Jovian system also serves as a model for understanding exoplanetary systems. Many of the exoplanets discovered in recent years are giant planets, similar in size to Jupiter or larger. These planets likely have moons of their own, and some of those moons might experience tidal heating similar to what Europa experiences. If Europa proves to be habitable, or even inhabited, it would suggest that similar moons around exoplanets might also harbour life. As you rest now, consider Europa's place in this grand cosmic context. It is not just a moon, but a member of a family, shaped by its relationships with Jupiter and its sibling moons. The forces that make Europa potentially habitable are the same forces that make Io volcanically active, and that have left Callisto frozen and dormant. Understanding these forces and how they vary across the Jovian system is key to understanding Europa itself. The Jovian system is a miniature solar system, a place where the processes that shape planets and moons can be studied in microcosm. Europa is one jewel in this system, a world of ice and hidden water, of geological activity and potential life. But it does not exist alone. It is part of something larger, connected to its siblings, and to Jupiter itself by bonds of gravity and energy and matter. Rest now in that sense of connection, that awareness of Europa as part of a greater whole. The story of Europa is also the story of Io and Ganymede and Callisto, the story of Jupiter and its magnificent magnetosphere, the story of tidal forces and orbital resonances, and the complex dance of gravity that shapes worlds. All of these threads weave together to create the environment that makes Europa so remarkable, so promising, so worthy of our attention and exploration. End of section 10. Word count, approximately 1,850 words, running. Total, 23,850 words. Section 11. Current and future missions. The exploration of Europa is entering a new and exciting phase. After decades of studying the Moon from afar, using data from the Voyager and Galileo missions, supplemented by observations from Earth-based and space-based telescopes, we are now preparing to send new spacecraft to Jupiter's icy moon. These missions promise to revolutionize our understanding of Europa, answering questions that have lingered since the first close-up images revealed its fractured, mysterious surface. The Hubble Space Telescope has played an important role in Europa research since its launch in 1990. Hubble's ultraviolet observations have provided evidence for water vapour plumes erupting from Europa's surface, a finding with profound implications for future exploration. If confirmed, these plumes would offer a way to sample material from Europa's subsurface ocean without needing to land on the surface or drill through the ice. The first hints of plumes came in 2012, when Hubble detected excess hydrogen and oxygen emissions near Europa's south pole. These emissions were consistent with water vapour being broken apart by solar radiation, suggesting that water was being ejected from the Moon's interior. Subsequent observations have provided additional evidence, though the plumes appear to be intermittent, not always visible when Europa is observed. The intermittent nature of the plumes suggests that they might be triggered by tidal stresses, erupting when cracks in the ice open during certain parts of Europa's orbit. This would be similar to the behaviour of plumes on Enceladus, Saturn's small icy moon, where geysers erupt from fractures near the South Pole. The comparison between Europa and Enceladus has become an important theme in planetary science, as both moons offer opportunities to study ocean worlds and search for signs of life. The James Webb Space Telescope, launched in December 2021, offers new capabilities for studying Europa. Webb's infrared instruments can detect heat signatures and analyse the composition of Europa's surface and any plumes that might be present. Early observations have already provided new data on Europa's surface chemistry, and more detailed studies are planned for the coming years. Webb's ability to observe in the infrared is particularly valuable for studying Europa's thermal properties. By measuring how much heat Europa radiates, scientists can learn about the temperature of its surface and potentially detect warm spots that might indicate recent geological activity. Webb can also analyse the composition of Europa's surface ice, looking for organic molecules or other compounds that might be relevant to habitability. But the most anticipated missions to Europa are the dedicated spacecraft now being prepared for launch. The Europa Clipper, a NASA mission, is scheduled to launch in October 2024 and arrive at Jupiter in 2030. This spacecraft will conduct a detailed investigation of Europa, making dozens of close flybys to map the Moon's surface, probe its interior, and search for signs of habitability. The Europa Clipper is named for the clipper ships of the 19th century, fast sailing vessels that made rapid voyages across the oceans. Like its namesake, the spacecraft will make repeated passes by Europa, swooping close to the Moon and then retreating to safer distances to avoid the worst of Jupiter's radiation. This flyby approach allows the spacecraft to study Europa in detail while minimizing radiation exposure. The spacecraft carries a sophisticated suite of instruments designed to address key questions about Europa. Cameras will image the surface at resolutions as fine as 0.5 meter per pixel, revealing details invisible to previous missions. Spectrometers will analyze the composition of the surface, looking for organic molecules, salts, and other compounds that might indicate habitability. A radar instrument will probe beneath the surface, searching for the boundary between ice and ocean, and measuring the thickness of the ice shell. The Europa Clipper also carries instruments to study Europa's interior and environment. A magnetometer will measure the induced magnetic field, providing more precise data on the subsurface ocean's depth and salinity. A gravity science investigation will map variations in Europa's gravitational field, revealing the internal structure of the Moon. And instruments to study charged particles and dust will characterize the radiation environment and any material being ejected from the surface. One of the most exciting aspects of the Europa Clipper mission is its potential to fly through plumes, if they exist and are active during the spacecraft's flybys. The spacecraft carries instruments capable of analysing plume material, including a mass spectrometer that can identify organic molecules and other compounds. If the Clipper can sample plume material, it could provide direct information about the composition of Europa's ocean, potentially including biosignatures if life exists there. The European Space Agency is also sending a mission to the Jovian system. The Jupiter Icy Moons Explorer, known as JUICE, launched in April 2023 and will arrive at Jupiter in 2031. While JUICE's primary target is Ganymede, where it will eventually enter orbit, the spacecraft will also make flybys of Europa and Callisto, providing additional data on all three icy moons. JUICE carries a complementary suite of instruments to those on Europa Clipper, including cameras, spectrometers, radar, and magnetometers. The two missions will work together, with their combined data providing a more complete picture of the Jovian system than either could achieve alone. The collaboration between NASA and ESA on these missions represents a new era of international cooperation in planetary exploration. The arrival of Europa Clipper and JUICE at Jupiter will mark the beginning of an intensive period of exploration. For several years, both spacecraft will be operating in the Jovian system, making observations and returning data that will keep scientists busy for decades. The questions that have driven Europa research since the Voyager era, questions about the ice shell thickness, the ocean composition, the potential for life, may finally be answered. But even as these missions are being prepared, scientists and engineers are already thinking about what comes next. The Europa Clipper and JUICE are reconnaissance missions designed to characterize Europa and assess its habitability. If they confirm that Europa is indeed a promising place to search for life, the next step would be missions that can search for life directly. Several concepts for future Europa missions have been proposed. A Europa lander would touch down on the Moon's surface, analysing the ice and searching for organic molecules or other biosignatures. Such a mission would face significant challenges, including the intense radiation environment, the need to land safely on an unknown surface, and the difficulty of communicating across the vast distance to Earth. But the scientific rewards could be enormous, providing the first direct samples of Europa's surface material. Even more ambitious are concepts for missions that would penetrate Europa's ice shell to reach the ocean below. These include cryobots, heated probes that would melt their way through the ice, carrying instruments to analyse the water and search for life. Some concepts envision submarines that would explore the ocean once the ice was breached, swimming through the alien waters and returning data on what they find. These penetrator missions are technically challenging and expensive, requiring technologies that do not yet exist or have not been tested in the relevant environments. The ice shell may be tens of kilometers thick, and melting through it would require substantial energy and time. Communicating through the ice to a surface relay and then across the solar system to Earth presents additional challenges, and the need to avoid contaminating Europa's ocean with earthly organisms adds another layer of complexity. Despite these challenges, work on penetrator technologies is ongoing. Engineers are developing and testing cryobots in glaciers and ice sheets on Earth learning how to navigate through ice and maintain communication with the surface. Scientists are studying the extreme environments of Earth's deep oceans and subglacial lakes, understanding the conditions that life can tolerate and the signatures it leaves behind. Each advance brings us closer to the day when we might send a probe into Europa's ocean. The timeline for such missions is uncertain. The Europa Clipper and JUICE must first complete their investigations, providing the data needed to plan more ambitious missions. Technologies must be developed and tested. Funding must be secured. Decades may pass before a probe enters Europa's ocean, but the goal is clear, and the path, though long, is being mapped. In the meantime, ground-based telescopes continue to observe Europa, and new space telescopes offer additional capabilities. The study of analogous environments on Earth, from deep-sea hydrothermal vents to Antarctic subglacial lakes, provides insights that inform our understanding of Europa. Theoretical models of Europa's interior, ocean, and ice shell are refined as new data become available. The scientific community remains engaged and excited, eager for the discoveries that lie ahead. As you rest now, consider the spacecraft that are even now journeying toward Jupiter or being prepared for launch. The Europa Clipper, with its solar panels spread wide, will soon begin its voyage across the solar system, carrying human curiosity to a world of ice and hidden water. JUICE is already on its way, beginning the long journey that will eventually bring it to Ganymede's orbit. These machines are our emissaries, extensions of our senses and our desire to understand. The exploration of Europa is a multi-generational endeavour. The scientists who analyse the Voyager data are passing the torch to a new generation, who will analyse the data from Clipper and JUICE, and that generation will pass the torch to another, who may one day see a probe descend into Europa's ocean. The story of Europa is a story of patience and persistence, of questions asked and gradually answered over decades and centuries. We are living in a remarkable time, a time when the exploration of Europa is transitioning from distant observation to direct investigation. The missions now underway or in preparation will transform our understanding of this remarkable moon, revealing details that we can only imagine today, and they will set the stage for even more ambitious exploration in the future. Exploration that may one day answer the question of whether we are alone in the universe. Rest now in that anticipation, that sense of being on the threshold of discovery. The spacecraft are being built, the instruments calibrated, the trajectories calculated. Europa waits, as it has waited for billions of years, its secrets locked beneath the ice. But we are coming, slowly but surely, carrying our questions and our wonder across the void. The story of Europa is far from over. Indeed, the most exciting chapters are just beginning.